All right. Welcome to today's live stream, everyone. We have Gabriele Carcassi um, presenting today.
Okay.
Yeah, go ahead, Carlo. Gabriele.
Gabriel, you can call me
Gabriele.
like in the English, I prefer. So, thank you for hosting me. So, what I thought I'll give today is just an overview of my project that is called Assumptions of Physics. We are going to discuss some of the results and some of the directions that we are going to achieve our goals. So, the main goal of the project is to identify a handful of physical starting points from which the basic laws can be derived. That's basically the whole scope of the project in one sentence. So, for example, the thing that we want to be able to say is that if we assume infinitesimal reducibility, we can recover the state space of classical mechanics. And by infinitesimal reducibility, we mean the ability to study a system in terms of subsystem. That is, I have a ball, I could throw the ball and study the motion of the ball. But then I could also take a red marker, make a dot on the ball, and study the motion of the red dot. And so the idea is that the system is infinitesimally reducible if studying the whole the ball is the same as studying all possible red dots that I could make at ever shrinking size. And that's the idea is that this should be an assumption that allows you to recover the classical state space. On the other side, we want to be able to say that the quantum mechanics is about systems that are irreducible. So we can take an electron, study the whole electron, but we can't take a red marker and make a dot on the electron and say we're going to study only this the motion of this red dot. And so the idea is that you can access the system and you can access the system as a whole. You can't half absorb a photon, you can't make a photon interact with part of the electron and so on. And so the idea is that we want to be able to say these type of things. And the problem is that to be able to say these things precisely at the end of the day, we need to rederive all the mathematics that we need, in the sense that if we only look at the higher level structure, but we do not know exactly what are the assumptions that are bundled into the low level mathematical structure, then you can't really do this program well, because you're never going to be able to clarify everything of what's going on. So, for example, at the lower level, one of the things that we want to be able to say is that science is evidence-based. That is, a scientific theory must be characterized by experimentally verifiable statements for which we have a test. And then the idea is that if we get this assumption, we can show that then we need to be able to have topological spaces as single algebra. That is the core structure that we have in mathematics are there to perform a function in physical theories, which is exactly the function to keep track of what is verifiable, what is connected to experimental evidence. So these are the type of things that we want to do. And sort of behind all of this, there is this perspective that I think it's always better to clarify. And so there is, let's say, this set is the set of all the things that really exist in the world, and we can talk about metaphysical reality. And these are things that philosophers like to talk about. But when we are doing physics, we are always constrained to physical reality. So things that can actually be accessed experimentally. And now, having been able to see and to touch something is not enough actually to do physics. We need something that is can be reliably prepared, reliably studied. In the sense, for example, we can talk about Napoleon or Julius Caesar. These are things that we have evidence for them, but we can't make a physical theory about Napoleon's and Julius Caesar's because these are not reproducible objects. And then the other added problem is that when we create a physical theory, the physical theory is not really technically about empirical reality by itself, but it's usually an analyzed account of empirical reality. We assume that things are isolated, things are deterministically reversible, and so there is some sort of idealization that goes from what we do in a lab to what we have in an actual physical theory. And to me, understanding these processes, understanding what is actually the requirement for our empirical reality and what is the process of abstraction and realization and how does it work. Those are things that are important because at the end of the day, you are going to see the effect of those things in the theory. And if you don't understand that they come from these requirements, then you might think that you're talking about something that really exists, which is actually you're just talking about what we can do in the physical theory. And so this sort of puts the project at the intersection of foundations of physics, foundation of mathematics, and philosophy of science, because you need to understand that when you have a problem, whether it's a problem in physics, problem in mathematics, or a problem in philosophy, and you have to make the correct identification, otherwise you're just not going to be able to solve the problem. And again, from this underlying assumption can this realization that if physics is about creating models of empirical reality, then the foundations of physics should be a theory of models of empirical reality, in the same way that the foundations of mathematics clarifies what is a mathematical proof, what is it that we can prove mathematically, and so on. And the foundations of computer science define what an algorithm is, what type of algorithm that you can have a classification of problem. Then the foundation of physics should be doing the same. And so from my perspective, we're doing something that is slightly different than from what people do in the foundation of physics. Typically, the people that work on the foundation of physics look for a physical theory that already exists, and they construct interpretation, clarifying some philosophical and practical problems, or they try to find a theory of everything, a theory that is always valid, in which all other theories can be seen as approximations. And again, this is not this does not correspond to the previous thought in the sense that the foundation of mathematics is not the theorem of everything, the theorem that proves all the theorems, or the foundation of computer science is not the algorithm of everything, the algorithm that proves everything, that calculates everything that can be calculated. No, it's just what we want to have is really a general mathematical framework that is a theory about physical modeling in the same way. So the idea is that we should have some general physical principle and requirements that are always there when you have to do physics. As I said, connection to experimental evidence. You always need to have that. If you have a theory that is not connecting to experimental evidence, then you say, well, this is not physics, in the same way that if you can construct a proof in a mathematical structure, that's not really mathematics. And so the idea is that these general principles and guidelines should give us a general mathematical framework, a framework that should be always applicable within any physical theory. And then other theories are found as specialization, as adding specific assumptions, you find the other theories. So if you are a mathematician, you can imagine that you have something like set theory that is always valid, and then you add the different, you study groups, so you study topologies, and then you have topological groups. But the things that you've proved at the level of sets are always valid. And so what we prove here in the general mathematical framework will be valid in classical mechanics, quantum mechanics, and so on. So we want to do essentially what you do in mathematics and computer science, push the theorems as high as possible, as abstract as possible, but this abstraction has to be guided from the physics. It can't just be some mathematical structure where you start studying the Grassmannian quantification of the Hopf vibration, whatever. It has to be coming from a physical assumption, from things that make sense from a physical perspective, and never go beyond that, because if you go beyond that, you lose the physical significance. So this is essentially at a higher level what our project is and how we want to structure it. And to achieve that, we have...
Can I ask a question?
Yeah.
Oh, is it okay by the way that I interrupt you, right?
Yeah. Sorry, I get it.
So this is essentially trying to solve the Hilbert-6 problem, right, of axiomatization of physics. But,
yes.
Right?
You can think it like that, yeah.
So, but you have to come up with a set of... But there's many ways you construct axioms in mathematics, and you prove things in that, right? You can also think about, do you use constructivism or classical mathematics? Are you actually constructing your theorems from your assumptions and axioms in a constructive way, or throw in your like exclude middle axioms and all things like that are not constructive, but barely some existential assumptions can be derived from that? So, right? Do you consider like that?
There are interesting issues there, and there is an interesting way of seeing things that puts what we need as sort of in between constructivism and the standard way the mathematics is done. So one way that you can say it is that sort of the difference between the constructivism and the standard way that mathematics, I don't know how to call it. It's what most mathematicians do that are not constructivists. They are only interested in things that can be proved, right? They're interested in what can be proved and not, let's say, what can be computed. Instead, the constructivists are more interested in what can actually be, in practice created, manipulated, and then computer. What is interesting is that in physics, we actually care about what is physically identifiable. And it has some feature of what is computed because experimental verification has to happen in finite time. And the composition that you can have can only be up to countably many things because otherwise you go away from the realm of finite time verification. But the fact that you don't have to compute allows the set of things that are interesting to be a little bit bigger than the one that is computational. In the sense, for example, you will know that let's say every function that is computable is topologically continuous, but not every function, computable function is topologically continuous, but the inverse is not true, that not every function that is topologically continuous is computable. Well, what happens for us is that all continuous functions are identifiable. So the space of things that you can sort of zoom in physically and say, okay, I think I'm zooming in on this function is bigger than the space of the one that you can actually compute. And if you're interested in the space that, again, the things that are identifiable, then the space is not quite the one that you have in computation, but it's not as big as the one that if you're only interested in proofs, because there you can make things that do not have a countable base in the topology that are far too big, and you wouldn't be able to narrow them down. So there are a lot of interesting things, and these are the type of things of why we say that I said before, that some of these issues are at the intersection of the foundations of mathematics and foundations of physics, because you need to take some ideas from basic computer science and foundations of mathematics, but then you have to adapt them to what the physicists need to do. I hope this made some sense.
So, I mean, it's all subsets. I mean, you're talking about physical phenomenon that we're interested in verifying empirically, right? So it's a physical phenomenon that can be reproduced using experimental apparatus, intersected with what can be verified using instrumentation, and in that intersection, still it's looking at phenomena that can be described using like mathematical proof or modeled using some type of mathematics.
Right. But the space of things that you can do where you can do mathematical proof is, let's say, it's bigger, right? If you assume axiom of choice and so on, you can construct objects that are at any level of infinity. And in physics, at most, you're going to be able to do a string of bits, right? You start measuring 1, 0, 0, 1, 1, 1, and you can imagine at most to go to infinity. And so the most that you can get of information is a countable set of bits. And with a countable set of bits, you're able to identify at maximum a set that has countability of the continuum, that is that has the size of the continuum. And so anything that is bigger than that, it's not going to be physically useful to any type of model, even idealized model, because it's really too big, right? But you do want the idealized model in physics, and so you are going to say, yeah, I want to pretend that I have that actual string of bits in my hand, even though I don't have it. But the subsets of the reals that you're interested in are the one for which you can at least imagine having a test. And I'll talk about some of these things at the end. What really is nice is that you can see that the assertions for which you have tests correspond to the Borel sets, which are very, very nicely behaved, and everything that we do in probability theory, measure theory can be done just with the Borel sets, and so everything works nicely. This is kind of one of the things that surprises the most when I started doing these things, is seeing how the physical requirements in the end were giving me mathematical requirements that were the nicest possible. And so a lot of generalization that mathematicians do that go beyond these requirements are actually not even useful for physics, because we can't realize them physically. They can't even be idealized, idealized representation of any physical system. So all our topology are second countable, which means when you go to the single algebra, all the algebra are atomic. All the points are singleton in the sigma algebra. It's like the simplest structure that you could have with those definitions. So. But I will come back to some of these things. I'll go through the reverse physics part, I guess, quickly, because if you guys have less of a background in physics, this is going to be probably less interesting. But the way that it works, again, is we want to be able to. Oh, I skipped to this slide. So I was saying there are two approaches to be able to do this. One is sort of taking the physical laws from the mathematical side and start to reverse engineering to understand what are the physical ideas that are there inside the laws that are equivalent. And because the idea is that we want to stop thinking about just mathematical construction, we want to understand the physics that is beyond that. And this has been increasingly getting worse and worse through the theory. I think that the last principal theory that we had was special relativity, where everything actually comes from first principle. Quantum mechanics, we just have a mathematical structure. General relativity, we have an equation that it's not clear where it comes from. It's the correct one, but you don't quite know exactly why you must have that equation. And then the field theories become even more esoteric. So I think this is one of the things that we need to do. But then, as I said, you need to restart from scratch, because if you're doing an axiomatic, you need to do the axiomatic from start, because in a sense, meaning and correctness can't be just sprinkled on top at the higher level. You have to do it from the fundamental level, layer by layer, and understanding what each pieces are. And it's a lot of work, because it means that you have to sort of look at all the definition of all the mathematical structure that we use and figure out what is the best way to, but it needs to be done. If we're not done, if we don't do it, we're never going to understand what quantum mechanics really is, because you have no idea what are the limitation of the tools that you're using to describe the theory. So let's go through reverse physics first, and all the things that I'm going to talk about today, they are written in an open access book. The way that I'm trying to set up the project, because it reaches a lot of different fields of human knowledge, I really would like to run this as an open source project. So the book is essentially a project on GitHub. Every time that I make a modification, it goes up there. And every few years, we create a new checkpoint with a new checkpoint version, where we add the major chapters that extend the whole project. So everything that I say is going to be in this book that is available online through our website or GitHub. So just to give you a sense of how it feels to do reverse physics, we can take the Hamilton's equation for 1 degree of freedom, which are this. The derivative of the position in time is the partial derivative of the Hamiltonian with respect of momentum, and the change of momentum in time is minus the partial derivative of the Hamiltonian with respect of position. What we want to do is to start finding conditions that are equivalent to these equations, so that we can start get a better idea of what these equations are describing. So one of the things that you find is that if you take this S and you understand it as a vector field, a displacement field that tells you where the states are flowing, you find that the divergence of this displacement is 0. And for 1 degree of freedom, if you set that the divergence is 0, you can find a stream function, what is called a potential for that flow, that then satisfies these equations. So this condition is equivalent to Hamilton's equation. And because the divergence is 0, what happens is that the area gets conserved, the Jacobian is equal to 1, and this is exactly another equivalent condition to the other. And we find others to sort of build up and there's better understanding of what happens to the geometrical structure. But then, of course, we want to turn these mathematical conditions in physics. We want to understand what happens to the physics. And in statistical mechanics, we know that we use volumes of phase space to count states. So if we have area conservation, what we are saying is that during the evolution, the state count is conserved. We're mapping areas with a certain amount of states to areas that have the same number of states. And this is basically deterministic reversible evolution. We're mapping states one to one. And note that it's not just a one-to-one in the mathematical sense, point to point, but there is a measure that we are conserving because the way that we count states on a continuum is through a measure. It's not through the cardinality of the set. And so this is, again, one of those points, and you need to have the math clear of what means physical. Another equivalent characterization of this, since we use the logarithm of the count of states to calculate and to define the entropy thermodynamic, then it means that area conservation means entropy conservation, and entropy conservation means that things are thermodynamically reversible. So this type of reversibility, which is mapping states one to one, is equivalent to the thermodynamic reversibility, which means keeping the entropy constant. You can find, if you use the information entropy, you find that the information entropy changes with the logarithm of the Jacobian, but if the Jacobian is equal to 1, then this part is equal to 0, and then you have conservation of information entropy. So again, deterministic reversible evolution means conservation of information entropy, which makes sense because if I give you enough information to identify a state at the beginning, then I gave you exactly the same amount of information that I need to give you to identify a state at the end. So this makes sense that determinism of reversibility is connected to conservation of information, and it's also connected in some sense to uncertain conservation. So, and the point here is that you see that the same set of the equation can be reinterpreted and seen in different ways. And I think this is the best way to see it. A lot of the time in the foundation of physics, people privilege one aspect, either mechanics or information theory. Everything is information theory and so on. And they try to rederive everything from one single concept. And what we find is better to understand that there is a connection between all of these. You get a much better picture. And so this is kind of how it looks in Hamiltonian mechanics. We have two basic assumptions: the deterministic and reversibility and the independence of degree of freedom. And these are all equivalent characterization of these assumptions. And then you put them together and you're going to get equivalent characterization of Hamiltonian mechanics. And this is also interesting from a technical point because mathematical conditions and physical conditions are not necessarily one-to-one, because again, the math was not designed to map exactly to physical conditions. So there is a sort of remassage that needs to happen. If we really had everything done right, then we would have that one physical condition mapped exactly to one mathematical condition and be able to do this. And we can't do it right now because, again, the math that is there, it's not quite what we want. But then once you're able to make this argument, to be able to see it this way, you can also start asking those philosophical questions like, could we have different laws? And the point is that, well, as long as we have something that adheres to these assumptions, then the laws are set. There's really nothing else that the laws are adding. So it turns out that the laws are actually a lot more constrained. And so one of the things.
Can I ask something here?
Yeah, go ahead.
Oh, maybe you're going to get into some of the details, but so are those in the previous slide? I guess are those meant to be fully equivalent expressions of Hamiltonian mechanics, or are they illustrating?
No, they're fully equivalent. So when I write these equivalents here, and I write, you see these statements that have the same prefix, these are really equivalent.
Okay, but so I mean, some of the 7 I am not an expert on, but it is certainly not true that all divergence-free flows are Hamiltonian flows.
Correct. This is qualified for 1 degree of freedom. If you're within 1 degree of freedom, it is. Okay.
So this is within the 1 degree of freedom. Okay, fair.
Right. And then you're going to see that this conditions, which was the same condition, is this dr only captures determinism or reversibility. It does not capture the independence of the degree of freedom. So if you now add this plus the independent degree of freedom, you get a joint condition, and this joint condition is equivalent to Hamiltonian.
Okay. So it is for the 1 degree of freedom case. Okay.
Yes.
Yeah.
Yes.
Okay. Sorry. Yes. Then
So
then it makes sense. Yeah.
Yeah. So the corresponding one, the one that actually generalizes, is that you take the flow, you rotate it 90 degrees using the symplectic form, essentially. That thing is kernel free. And that's how we get the potential from the Hamiltonian. So that's kind of how it works. Yeah.
So I get a meta question on that is because obviously saying we are in 1 degree of freedom has, I mean, some people might say, well, but the mathematical structures live in their corresponding categories where you don't really see 1 or 2 or 3 or 27 dimension, right? Like you see the more purely axiomatic assumptions, and sure, like part of it is dimensionality, and it's not. I mean, the dimension is not irrelevant mathematically, but one, especially if one is coming from the perspective of Hamiltonian mechanics, you know, the kind of structure that go with it and so on, one typically has a much more dimensionally agnostic perspective. At least I did when I was studying all these things, and most of my colleagues in the sort of Poisson geometry field are much more sort of dimensionally agnostic. So my question is there a reason to make this distinction, or is it just a case of illustration for saying 1 degree of freedom? Or...
So from a didactic point of view, you can understand a lot more just by focusing on the 1 degree of freedom and then generalize.
Sure.
Like the 1 degree of freedom is critical to understand some of these concepts, so that then they're always going to be there. And it's a perfect illustration of these. And then, of course, you're going to write things in a way that it's generalized to multiple degrees of freedom, where there is an n and you don't care what the n is.
Right.
But it's a lot. It's very useful to study the simple cases first and map those completely. And once you have mapped those completely, mapping the generalization is a lot easier.
Okay, sure. Yeah.
As an example for this is exactly the next slide.
Okay, yeah.
This is the explanation of the principal list action. And we do it for 1 degree of freedom, because in 1 degree of freedom, you can use the tools of vector calculus that most people do. It gives you the right intuition, you understand what it was, and then you can generalize it. But to generalize, you have to know differential topology, which most physicists don't have. But you can understand what's going on just from here, and it's a lot more useful. So for those that don't know what the principle of list action is, another way of expressing Hamiltonian mechanics is through a Lagrangian, and you integrate this function of position and velocity over a path, and then you look for the paths that minimize this quantity. And this is introduced as one of the guiding principles in classical mechanics, but it's never really understood why you have it, what is it doing geometrically, and so on. And this is sort of the explanation. So we're looking at position and momentum and time. So all the states are sort of moving to the right. You have this flow of states that continue. And the assumption of deterministic reversibility means that these states are never created and never lost. That means that the flow is divergence-free, it's incompressible. And if the flow is incompressible, it's divergence-free, then you can find a vector potential whose curl is the flow. You stick a minus sign for some to match convention, and then what you can actually prove is that because the flow in time has to be unitary, and because in every curl you can pick a gauge to make things simpler, you can always express this as these 3 components, P, 0, and minus H. And if you take this, and when you're doing a line integral on any lambda, on any gamma, if you take a path gamma and you do the line integral of this vector potential, what you're going to find is that you're integrating the Lagrangian in time. And so what you can really understand is that the action is really the line integral of the vector potential of the flow states, which isn't physical. In fact, it's known that the Lagrangian for a system is not unique. You can have different Lagrangians, and what you're doing is just changing the gauge of this vector potential. But then why we're interested in the minimization of the action, why the variation of the action is to be 0? Well, because if we take a path and a variation, and we do the integral of a path minus the integral of the variation, what we are doing is actually the integral, the integration of the line integral of a closed curve. And now we can use Stokes' theorem, and we can see that and what we are actually calculating is the flow of the fields between the path and the variation. And so if we're interested in paths that actually describe the evolution of the system, these paths are always tangent to the flow. And so they're never going to be able to catch any flow. And so the flow between a path and a variation is always 0. And so, of course, we probably need like 10 minutes to go and through there. But the point is that this has a very simple geometrical mathematical explanation. It's not, it doesn't come out of nowhere. And the most interesting thing is that this sort of geometrical understanding works even in the cases where there is no Lagrangian, in the sense that you can express this integral, but you cannot express it as a function of position and velocity. You can only express it as a function of position and momentum. So really, the real geometry that happens is in the geometry of Hamiltonian mechanics, and the Lagrangian mechanics is just sort of another reiteration or representation of that. It's not really adding any other anything else. So this is more or less the assumption that you have in classical mechanics. There is this idea of infinitesimal reducibility that basically allows you to talk about the infinitesimal particles. There is a notion of independence degrees of freedom, where the count of total states becomes the product of the count of states in different degrees of freedom. This is going to give you the classical phase space. From the classical space you add determinism and reversibility, you get Hamiltonian mechanics. From Hamiltonian mechanics, you get an extra assumption, basically saying that states and trajectory in space are equivalent. If I give you the trajectory in space, you're able to reconstruct the space and vice versa. If you have this, so then you're going to be able to reconstruct Lagrangian mechanics, and you're also going to get the Hamiltonian for massive particles under potential forces. So the idea is really what comes out of this is that the laws that we have are actually much more constrained than one would think. And they're really a simple, well, maybe not so simple, but they're an application of simple complex, so for simple concepts. And these assumptions that might seem sort of very, very easy vanilla actually have a lot more consequence that you would think. So yeah,
can I quickly ask from it, because I had some connectivity issues and I missed the very beginning of the talk. So so I think I understand all this rectangles in most of the screen, except for the leftmost, the infinitesimal reducibility and the degree of freedom independence. So can you very quickly summarize what these mean?
Right. So infinitesimal reducibility, you basically say I have a system, and the system can be thought of parts, and parts made of parts, parts made of parts, and so on. And studying the whole is equivalent to studying all the possible parts.
Right. So am I right to understand that this is what leads you to consider something like a smooth manifold as your state space?
Yes, that's exactly what it gives you.
Okay, good. And then what about the degrees of freedom?
The degrees of freedom is the ability to do this count of configurations in a way that, let's say, they're unit independent from the other. So if I say that it's better to do it in reverse. If you take a position of momentum, right, and you multiply them together, you get areas that are invariant, in the sense that if you change position, the position is going to change in one way, the momentum is going to change in the opposite way, and the area are going to, when you do the multiplication between the dq and the dp, the change cancel out, and so the area in phase space are invariant. And so the idea is that if we want to really be able to talk about state and density over states, we need to have these count of states that are invariant. And the independence of the degrees of freedom means that counting states on one degree of freedom is independent from the other. You have all the possible configuration. If you fix a variable in one degree of freedom, you are not going to constrain all the other degrees of freedom. So if you think it in the discrete, if I have 3 configuration on one side and I have 2 configuration on the other side, then they're independent when I have 6.
Yeah.
So basically, it means it's uncorrelated, right? So it's like
it's
can
more
be-
than uncorrelated, because uncorrelated is a property of probability distribution. Well, this is really a property of the variables. So I don't have it. Do I have it here? No, I don't have it here. But my classic example is if you think about a rabbit farm, you can imagine the population being described by the number of males and the number of females. Now, these are independent quantities because you can have any combination. But you could also use the total number of rabbits and the female rabbits. And now these are not independent anymore, because if I tell you there are 230 female rabbits, well, you know that there are at least 230 total rabbits. So you don't have all the possible combinations, and so the elements are not, the variables are not independent. Well, it turns out that the ability to have statistically independent distributions on the two variables coincides of having variables that are independent. That is where you can make all the combinations. So the independence, if we go back to this, right, the independence has a bunch of different characterization. One of them is the composable in this independent degree of freedom, which means this. I define the unit on one degree of freedom, don't affect the units of the other. I count things on one side, it doesn't affect the other. And then where the system allows statistical independent distribution of each degree of freedom, well, this is equivalent to doing that. And it's the same thing for having informational dependence, the fact that the information entropy sums for a particular distribution, the information of the joint is the sum of the margin. And so again, all of these are explained to all these details in the book, but it's really a matter of getting all these details right.
And then just to understand this last one, so is it right to say that if this infinitesimal reducibility leads to the concept of a smooth manifold and continuous topological space, whatever, yep. Is it fair to say that the degree of freedom independence leads you to consider that your manifold is going to look locally like a Cartesian product of this one-dimensional variables? And furthermore, you have a volume form that is going to be invariant there.
You have a symplectic form. So this
that's what's bringing the symplectic form. Okay.
Yes, the symplectic form is what it allows you to count the configuration for each independent degree of freedom.
But that's introducing a notion of duality between degrees of freedom, right?
What do you mean duality?
Well, because I mean, a symplectic form. So my understanding is that if you want to say that you have independent degrees of freedom, this to me look like dimensions of your space that you can measure, right? That your space is not just topologically continuous; it's actually manifold-like and is locally diffeomorphic to some Rn.
All right. Yeah.
But if you say that it's symplectic, then suddenly it has much more structure, right? It has to be even dimensional. It has this collection of variables and this what I call dual, so conjugate. I think
conjugate. Yes, yeah, it's a conjugate. Yes.
But I fail to see how degree of freedom independence, at least as a term, as a concept, leads into a symplectic form.
Right. Well, I can talk about for half an hour. The quick thing is again, you want these count of states to be independent from the definition of the units that you use between position and whatever everything. So when we are here, we don't even know the Qs are positioned. We just the way that the Qs are picked out are the Qs are the variables that define the unit system.
Yeah.
And then what happens is that if you want to have a degree of freedom that is independent, then you have one unit that defines the unit system for that degree of freedom.
Yeah.
Then you have the unit of the count of states that has to be independent. And then the only way to do this without introducing extra flexibility in the unit system is just to add another variable with another units, who is the count of degree of freedom divided by the unit of Q, and there is no other way.
I see. So I find this, by the way, the reason I'm stopping here is because I find it fascinating. I mean, I worked on this for a bit when I was doing my PhD. I worked on trying to justify why symplectic structures were the right thing to choose. So I'm very interested in this particular question. So because I know that we're jumping to the quantum one, I find it super interesting what the difference is between the classical and quantum.
So what you might want to do, if it would be useful for me, if you go read a book and then see if the arguments there are convincing, and if not, you you said this,
Yeah.
but I don't buy it, or whatever.
Yeah, no, but I'm not coming from a position of like, I'm not buying this at all. In fact, what I'm trying is to understand fully the argument here. So, so just last comment, and then we move on. So you say that you want to, intuitively, you're introducing conjugate variables because you want to compensate pairwise, right? Like in this way.
Yeah, because it's the only way to do it. Yes.
Right. So how do you play then with the fact that you have several Qs and several Ps, right? Like, I mean,
it's the independence of the degree of freedom. So you have n variables that define units. So you basically say up to here, you basically say, okay, I know that I have a manifold and I have a differentiable structure, at least because I need to be able to define these volumes. Otherwise, I can't do I can't define densities over a point. So you need to be able to do that. And also you need to be able to define this density over a point over a counter space. So you're going to have at least a volume form that tells you how many states you have there. Perfectly fine. And then you have independence of the degree of freedom. And what you're going to say is that, look, my manifold is n-dimensional, and there are going to be k variables that define the unit system. And all the others are going to be derived units.
Okay.
And then you say, okay, I pick one, I start picking one, and I say, okay, I need to be able from to make a unit transformation on only this one and keep the volume the same.
Okay, I see. I see it now. Sorry. Yes. I was just warming to the idea. I see the argument. I like it a lot. So yeah.
And this is the crazy thing. It's all about the unit system, which is something that mathematicians throw away. But
absolutely,
actually, the structure is there to make sense of the unit system.
That's great. No, I mean, my thesis was exactly on this, on putting a unit system on top of symplectic manifolds and so on. So cool. I love that. But I'm fascinated because I never really saw this angle of argument where you're basically anyway.
I've never seen it here.
Let's continue because
I've never seen it myself, right? I had to make it up, and
no, that's great.
And it's part of the game. Like the thing that I find most fascinating about this is that you're looking for argument, and so you start generating a bunch, right? And when you generate the argument, even if it's correct one, you're not going to believe it because you haven't used it enough in your head to make sense of it. And then you use it a little bit more and more. So, actually, and then you use it more for other things. And when you start saying that argument that you were skeptical about, but then you're able to do all these things and say, okay, I'll buy the argument now. And so it has been a process. So yes, please go read the book.
Absolutely, I will. And I'm super interested to see how the quantum goes.
If I knew that you guys were interested, I would have I have other slides for these things and so on. Anyway, yes, move on. Otherwise, we're not going. So one of the things that that also reverse physics allows you to do is to see the connection, not just between different ways of seeing the same physical theory, but across physical theory. Because you say, okay, we have just proven that if we assume deterministic and reversible evolution, we get existence and conservation of energy. And you say, why that should bear this length? And then you think about it and say, well, if I have deterministic and reversible evolution, the past and future depend only on the state of the system. It means that the evolution does not depend on anything else. If it does not depend on anything else, well, the system is isolated. But if the system is isolated, there is the first law of thermodynamics that tells you that the system will conserve energy. So you can make already an argument from deterministic reversible evolution to system conservation. So what happens is that this is essentially a stronger version of the first law, because not only tells you that the energy is conserved, it tells you that an energy has to exist if you have this structure. And these are the kind of things that I look for, like things where you think that these theories are disconnected, instead they're actually connected. And one of the things that I like doing is the classical analogs of quantum mechanics. So we're going to look now at what I call the classical uncertainty principle. So one of the things that you may or may not know is that Gaussian states minimize uncertainty at a given entropy. So if I have this graph where I have uncertainty here, and entropy here, right? If I fix an element of entropy, right? If I say entropy 1, this is going to be the lower bound on the uncertainty, and it's going to be given by a Gaussian state. And this is both true for both classical mechanics and quantum mechanics. So this is the bound for classical mechanics. And this here is the bound on quantum mechanics, and you can see that it stops here at h bar, while the bound on quantum mechanics can go farther and farther, and you can get states with negative entropy, because now your Gaussian becomes so small that it's you could get less than a unit of volume phase space. Okay, so these states of negative entropy, of course, they do not make sense because they don't make sense using the third law of thermodynamics. So what you can do is say, okay, let's define H to be the volume of phase space over which a uniform distribution, a classical uniform distribution, has zero entropy, right? And so we were going to be here. But this is a uniform distribution, it's not the one that minimizes the entropy. So you look at the Gaussian. Now the Gaussian is going to have a spread of H over 2 pi E. Well, H over 2 pi is H, as h bar, therefore we have uncertainty of h bar over E, and E is a little bit more than 2, and so the uncertainty can be a little bit less. So the point here is that if we put a lower bound on entropy, we should put anyway, because that's the third law, we get a lower bound on the uncertainty in classical mechanics as well. And it really looks like one of the bound that you have in quantum mechanics, because again, the uncertainty relationship is saturated by a Gaussian state, like exactly in quantum mechanics. So one way that you can look at all of this is say, okay, I have
a question here. It's like, but can you do it the same kind of argument for the classical uncertainty, but instead of Gaussians, make some finite dimensional distribution? But still keep it classical.
If you have finite dimension, you mean a distribution of a discrete
discrete set of discrete variables, discrete random variables.
So the discrete, the one that minimizes the uncertainty is going to be the uniform distribution over one element. Yes. So you're going to have uncertainty on 0.
So you have to go to the continuous.
You need the continuous, yes. So the idea that I think of quantum mechanics is really putting a floor of the entropy or the count of states for the continuum. And that's essentially what's happening. We're going to see it later.
Would a noise floor be accurate to say?
You can think it as a noise floor, yes. You can think it that there is some kind of noise, background noise, so that the vacuum is not really empty. There is it's the 0 level of noise, and that's one way that you can think about it.
Yeah. So for the classical case, you don't have this floor even for finite dimensional systems. But for the quantum systems and even the finite dimension, you have to put this floor, like for spin. There's a lower uncertainty bound.
Yes, but the way that so I don't consider quantum mechanics a discrete theory, in the sense that if you look at the state space, it's always continuous. Like it's if you even just look at a two-state.
It's like a distribution. It's like the value for the probability is continuous, but it counts the finite number of states.
Right. But so if you think about the block ball, right, the state of a pure state is the sphere. You have still the set of pure states has cardinality of the continuum.
No, that's the same for the classical probability. Like you take a simplex one-line distribution, it's still continuous.
No, the pure states are two. The pure states are two.
Well, the pure states. Well, with the pure states is just those states with the highest bound, or the bound is reached essentially of uncertainty. Those are the pure states. Right. They don't necessarily correspond to some like extremal points on your probability simplex.
Yeah, but the point is that in the classical space you have two states and you connect them by a line. In the quantum case, you have a sphere and then you connect the center and you get the ball. In the classical discrete, you start with two things. In the quantum case, you start with a sphere. It's a manifold.
But you can wrap the sphere with the probability simplex, and you get a finite dimensional finite number of states, right? And you can describe the probability every quantum state with just the usual discrete probability, right? It's like in classical. In quantum information is basically the same as measuring with POVM basis, right? It's just a set of measurement which just gives you all the values or probabilities that describe your state completely. So you can associate every quantum state on a block sphere with just a probability distribution over 4 values, 1-to-1, right?
Like you're talking about some, quasi-probability Wigner distribution type thing.
Not it doesn't necessarily have to be quasi distribution, right? You can expand your basis, which will fit all the states in the simplex, and that will describe any state as a distribution without any negative numbers, right?
How can you how can you turn a ball into a simplex? It's a ball.
You're not turning it into a ball. You wrap it around so that the sphere is in the block sphere is in sphere of the tetrahedron.
Okay, so therefore you're going to have some convex combinations that are not in the block sphere. Right?
Yes, because you have the lower bound. There are some definite states that are in a tetrahedron but are not valid quantum states.
Right, and then you're not going to have the correct entropy relationship. You're not going to be able to use the Shannon entropy on that.
Yeah, you don't have to, but yeah, it is like completely different notions of entropy, but just quantifying the uncertainty, that's kind of free to do. You can use the...
Right, but as I said, it's yeah, you can use affine coordinates for any vector space. At the end of the day, the block ball is a vector space, but it still remains that if you take the set of pure states, the set of pure states is a continuum. It's a manifold. It's not two discrete points.
But for me, the probability simplex is also a continuum then. It's like there's no difference.
Yeah, but there are some special points. Even if you put things in your tetrahedron, you have a boundary, right, in which that you go through, and you go from valid states to invalid states, because you're going outside of the ball, but you're still the tetrahedron. So you still need to take account of that. And even if you're in a tetrahedron, at least you're going to have 4 points. So it's still, more than 2. I don't know. It's topologically completely different.
Topologically different, that they're even diffeomorphic to each other. So, well, I have like a bunch of pictures. It's like I'll have to talk about this particular topic, but maybe now it's not the time.
Okay, so anyway, the point still remains. The set of pure states are not more in classical mechanics than in quantum mechanics. In quantum mechanics and classical mechanics.
Oh yeah, because you're considering continuous distributions, not definite ones for the classical. For me, it's like a qubit is indistinguishable. Is basically indistinguishable from some tetrahedral die that you can just throw around, but with some bound on uncertainty. You can just have a loaded 4-sided die.
So the way that I think of a qubit, I think it always a spin 1/2 system. The state of a spin 1/2 system is fully defined by a direction in space.
No, that's a projective measurement, but there's like a different kind of measurement.
No, in terms of preparation, I need to prepare a spin 1/2 system. I rotate my device, and by rotating my device, I can reach all the possible pure states.
So your rotation, your axis, choice of axis, your observable only defines half of the qubit, right? Because as you said, there's also conjugate variables. There's also
I'm preparing a pure state. Right? I have a device that prepares spin up.
Yeah.
Okay. I can rotate the device 180 degrees. Now it's preparing spin down. I can rotate it 90 degrees, and now it's preparing spin right. Just by rotating the device, I can choose. I can explore all the possible states.
Sure, you can also rotate a tetrahedron. Well, we can debate.
Okay, let's continue. So so we get this classical bound of the entropy, and so the idea is that if I have the third law of the thermodynamics, that gives me a lower bound of the entropy. Quantum mechanics already had the bound of the lower bound of the entropy, and it therefore gives me an uncertainty principle. And the classical mechanics does not have the typical bound of the entropy, but if you add it, then you're going to get an uncertainty principle. And so you can basically say, okay, I can make the argument that the uncertainty principle is really a consequence of the third law. It's not really a quantum mechanic things. It's already embedded in the third law. And then you can say, okay, well, do I need the third law? Is it something that is just experimental, or there is good reason to think that there is? And this is where I call this principle of maximal description. It's kind of a silly name, but the point is that if you assume that the entropy is additive for independent system, then if I have a system that has nothing, like a gas with zero number of particles, then the entropy of that system has to be zero, because if I add the system to itself, it's the same as the system to begin with, and therefore the entropy has to remain the same, and therefore it has to be zero. I know if you think about it in sort of information theoretic terms, if I had a state with an entropy lower than my empty state, more than zero, I would basically saying that I'm describing the state more accurately than saying that the system wasn't there to begin with. And then, of course, that doesn't quite make much sense. And you can make other arguments for which negative entropy don't really make sense at a conceptual level. So at that point, if you like the argument, the third law becomes more than just an experimental law. It's really a conceptual law. It's something that you can't violate on conceptual ground. And so one of the things that we want to try and push forward is this the only thing that is happening in quantum mechanics or not? And of course, we don't have the full thing done mathematically, even though we're getting very close, because we're working on a paper to actually recover classical mechanics as a high input limit. But the point is that the way that we can think about these two things now is that in classical mechanics, we can reach any entropy that we want. We can make this thing as shrink as we want, and we can in principle go below the zero. But in quantum mechanics, we can't go below the zero. And so if we can't go below the zero, as we saw also in classical mechanics, we're going to have an uncertainty. We're going to have simply, we can't squish everything because we are on a continuum, and therefore the entropy zero means that there is a minimum uncertainty. Now, if we have a minimum uncertainty in space, then we must have that we are going to have non-local objects. Because if we were able to say, okay, we can interact with only the part of this object that is here, we would be interacting with an ensemble that is better specified than the entropy zero. And we can't do that. Therefore, if we're going to interact here, we are actually interacting with the whole thing. We can't interact with the part. And then you're going to say, okay, but can we use this to make some communication that is superluminal within and see what happens in the quantum? Well, if you were able to do it, then you would be able to know what is happening within that ensemble. And again, you can't do it because otherwise you would be able to have access with ensembles that are more refined. And so the point is that there are a lot of things that the argument that you can do in a qualitative level, even just of thinking essentially of the classical mechanics when you're cutting the entropy, that really remind you of quantum mechanics. And so there's a lot of things that we can recover, that at least qualitatively, where we can recover the whole field quantitatively. That's a different problem, and it's still open. But at least as an intuition, you can get the same intuition, and you can use.
Can you perhaps maybe add more about this inability to refine ensembles, and what does it mean? It's like permutation for me intuitively. It's like if you have some ensemble, like maybe some set of particles, having some random values for their variables, you can maybe permute them around. That's not going to change your information. That's allowed, right? But refining your ensemble, it's maybe adding some noise or somehow removing the noise, changing information. That's what corresponds to refining it, right?
Right. Refining an ensemble means taking an ensemble and seeing it as the sum, as the convex combination of other ensembles. And whenever you're going to do that, the ensembles that you're combining to make the total one are going to have lower entropy. And so you access parts of the ensemble by having ensembles that have a lower entropy. So you have a probability distribution that is like this. You cut it in half and you say, okay, this probability distribution is this part plus this part. And now I'm going to only study this part. And if you say I'm going to only study this part, it means that that ensemble is accessible to you. And so it's more refined.
Maybe step one, make one step back. It's like, and define what an ensemble means. What exactly?
An ensemble is the collection of a preparation procedure of all the possible output of a preparation procedure taken as one. So you have a something that preparing some states, and you have a procedure that you follow to prepare those states. So the ensemble is the collection of all the states that that thing prepares.
So what would be the example like for classical system for the quantum one?
For the quantum one is a density matrix. For classical mechanics, a probability distribution in phase space.
So you identify the probability distribution in the quantum states is like an ensemble.
No. The density
It's like you can
matrix,
sample and make a.
the
It's like
density
sampling.
matrix is ensemble.
Yeah. And the probability distribution is not an ensemble, but when you can sample from it some set of microstates, that's the ensemble. That's what you call an ensemble in classical sense.
In classical sense, is a probability distribution over phase space. That's a classical ensemble. This is just standard statistical mechanics term. I didn't define it. So if you have, you want to calculate, I don't know, thermal states in classical mechanics, you pick some, what's it called, Hamiltonian. You maximize the entropy. You find the distribution that maximize the entropy with the constraint of the Hamiltonian, and then you find the Boltzmann distribution. That's an ensemble.
Yeah. So it's basically some region of the phase space, right?
It's a probability distribution again. It's
yeah. But I'm just trying to clarify this connection between the classical and the quantum, because for me it's still unclear. It's like, because for me the point on the block sphere is kind of the same as probability distribution, so it's a point in the phase space.
No, it's not. No. Okay, the point of a block sphere is like a distribution of phase space.
That's what's confusing. It's like
well, they're ensembles, right? So what you can do with two probability distribution is you can make a convex combination. I'm gonna take 20% of the time this probability distribution and 80% of the time the other probability distribution. And so you do rho 1 times 1/5 plus rho 2 times 4/5. And you get a new distribution. And that's the mixture of the previous two distributions. And as you do the same thing in quantum mechanics, you take two density matrices and you do the convex combination. And density matrix for a two-state system, they become the points that are the interior of the block ball. And so you take 2 points and then you take the segment between them and you pick one of the elements that are inside.
And you get another distribution. It's like
and you get another mixed state, yes.
Yeah. Hold on. But when you make two systems and you correlate them with each other, it's like correlation in the classical sense, it should be the same as entanglement in the quantum sense, right? So you take 2 points on the block sphere and taking them together may be correlated.
No, for that you need the product of the spaces. Yeah. So you need 1 degree of freedom and another degree of freedom. You make the product, and now you're going to have the adjoint distribution in classical mechanics and the marginal distribution.
Sure.
In quantum mechanics, you do the same thing. I have one Hilbert space, the other Hilbert space. I take the product, or I do the tensor product, and then the mixed states on that tensor product become the ensembles of quantum mechanics. And good luck visualizing that, because it means that at least you're multiplying 2 to, and so you have a projective space, you have a Hilbert space of dimension 4, and the visualization of that, it becomes it's basically the tetrahedron, and then for every point you have like a 3 torus, right? You have the product of 3 circles for each point at the inside of the tetrahedron. So my head exploded, but in principle it's still a convex space.
Yeah.
So the points in phase space are the equivalent of of the points of the surface of the block ball, right? So the point in phase space, you can kind of think them as the pure states of classical mechanics.
Then why mixed states are not points on the phase space?
Because if you take just a point, you have a 100% distribution over a single point. It's not an ensemble.
But it corresponds to, you can, that's a quantum state, right? It's non-deterministic state. You can talk about like observing it and measuring, because it corresponds to some kind of distribution, right? Therefore, it has to
The
be
point
related
of
to-
phase space is just a point. It's not a distribution. I don't understand why you keep saying that points in phase space have distributions.
because there's like one-to-one map. It's like there's a Wigner distribution and the density
Oh,
matrix.
but the Wigner distribution, as I said, it's a completely different thing. That's what I asked before. The Wigner distribution, first of all, again, the points in phase space for Wigner, they're not distribution.
They're equivalent distributions that are actually not quasi. They're actual distributions, if you smooth it out.
Yeah, so you can just get the Husimi distribution, which is basically it's doing the same thing, and it's always positive. But the point is that those are not really probability distribution; that they work in a different way. And still, if you just
the equivalent way for the qubit, you can do the thing equivalent to the qubit, and they work exactly as distributions. I don't understand what's the difference.
I don't think we're making progress, so I don't know. If you guys want to, I can keep talking about this, or we can see other.
Yeah, let's continue here. I mean, we can come back to this.
Yeah. So I'm not even halfway through, so.
Yeah.
So I don't know how fast you guys want me to go. So one of the things that we like thinking about both in classical mechanics and quantum mechanics as processes, as things that take ensembles and take out and give you as an output an ensemble, because this now any process where there is deterministic and stochastic can be modeled in this way. And they have to preserve the convex structure. So if I have a process and I apply it to a mixture, then the output is the mixture of the outputs of the process. And so this is something that again has to be always valid. And then you basically say, well, now I want to determine an evolution that is deterministic and reversible. What it means is that you have a way to undo the process, either because you're really running it backward, or simply because you're able to reconstruct the original system. So you still need to be able to have an inverse. And since you have an inverse, what's going to happen is that this is going to correspond to unitary evolution, just by definition. It's going to be the thing that you're going to have. So deterministic and reversible evolution in quantum mechanics becomes unitary evolution, and there is no surprise there. For measurement, what you can argue is that a measurement has to be repeatable, in the sense that if I take the output of the measurement and I do it yet again, I need to get the same the same output. And this means that I have an evolution that is linear and it's idempotent. And this is the definition of projection. Projections are linear operations that are idempotent. And the way that it works, then the quantum measurements, what they're really doing in this, like looking in this way, they're taking points, let's say on the whole block ball, for example, here, and they're giving you the output, which is what you can predict that is going to be there after the measurement. What you can predict that is going to be there after the measurement is going to be a probability distribution, so a classical probability distribution between the outputs of the measurement that are going to be the eigenvectors. They're going to be the stable states of the process, and so they're going to take essentially any point and project it here on the axis. And then once you actually go and look at the result of the measurement, you're going to basically say, okay, I was here, this was my prediction, now I know that I have this state or that state. And that becomes really just a classical update. There's nothing else that happens at this point, because you're already in a classical space where you project it to this slide. And then you're going to have the same problem and say, okay, well, we have these two things, and we can't really think about the projection as a unitary process, because this thing always conserves entropy. This clearly does not conserve entropy. Here I'm going to mix states, so therefore I'm not conserving entropy. But then what you can do is thinking about it in the opposite way. Well, if not, if a projection can be explained as unitaries, I can explain unitaries as projection, as basically a projection that become infinitesimal, and they're becoming so small that instead of projecting from up to left right away, we're essentially projecting in the middle for ever slightly increasing steps, and then we are going to make the evolution unitary again. So this is how we disentangle this, and again, it means prioritizing this type of measurement, not collapse, projection, right? And then you're going to say, okay, well, what are these things? Like, is there a way that we can find, again, parallel in something else, or it's something that is just in quantum mechanics? Well, again, as I was saying before, the eigenstates are the states that are unchanged by the process. And we already have, in terms in physics, for a state that is not changed by a process, it's just an equilibrium. It's the input state is equal to the output state, it is an equilibrium. And what you can show is that every state is an eigenstate for some unitary or Hermitian operator. That is, all pure states are equilibria of some process. And you can also make the same argument for mixed states. And so if you say, well, everything is equilibria, and then we have this measurement that we go from one set of equilibria to another set of equilibria, well, we can go and make a parallel to what happens in statistical mechanics and thermodynamics. If I have a cup of water that is open, this is a grand canonical ensemble. I hope I get the name right. And in a grand canonical ensemble, you have three variables that are well defined: the temperature, the volume, and the chemical potential. And the number of particles is not well defined because it's jiggling around. So you have a probability distribution on the number of particles. But then you say, okay, now I really want to count the number of particles. Well, you need to have something that keeps the number of particles the same. Otherwise, you don't even know what you count. So what you do, well, we can close the lid. I close the lid. I go from a grand canonical ensemble to a canonical ensemble. Now, this is defined by number of particles, volume, and temperature. And of course, since I closed the lid, I don't know exactly what the number of particles were because it was jiggling around. But once I fixed it, now I'm going to go from a single sort of equilibrium of thermodynamics over a distribution of equilibria with the different number of particles. And then I can go count my particles and say, aha, I know which one I have. And so we're going to essentially, by changing here, we go from states where a set of variables are defined to other states where other sets of variables are defined. Now the number of particles is defined, the chemical potential is no longer defined. And so this is essentially what happens, say, during a spin measurement. I prepare a spin in a particular direction. I do something. I constrain now the spin to align from up or down. The vertical direction of the spin was not well defined before. It needs to select it. It's going to go, let's say, a phase transition from one set of equilibria to the other. And now the other variable is what's not undefined. And so the idea is that this projection can really be thought as equilibrations, and the unitary evolution as a quasi-static process, exactly in the same that we have in thermodynamics. So the idea is, these are nice ideas, they make sense physically, we still need to turn them into math and make them rigorous in the same way that we did for the reverse physics of classical mechanics. I think I have to go a lot faster if I want to go through the other things. The only thing that I want to say here that is interesting is that, again, we typically have the idea that thermodynamics and statistical mechanics are built on top of mechanics. What we find instead is that the entropy is essentially equivalent, both in classical mechanics and quantum mechanics, to define the geometrical structure of the theory. So either I give you the way to calculate the entropy, and then you can go and reconstruct the geometrical feature of classical mechanics or quantum mechanics, or you give me the geometrical entity, the symplectic form or the inner product, and you can go and reconstruct the entropy. So really, the geometry is the entropy in physical theories. And I'm going to skip that. And so let's go through a little bit quick from some of the idea that we have on the other side, where we want to really do the axiomatic. We really want to start from scratch and layer things on top. And one of the reasons why we want to do that, and it's sort of novel, is because what happens right now is that people always think that somehow the math comes first and the physics can be derived somehow. So if you go to Wikipedia in the mathematical physics section, you find this picture in which there is the math that is everything, and then you have some kind of lesser math here, which is mathematical physics, and you have an ontology that comes from the math, and I really don't understand what that means. And then you have physics here, that it's sort of, it's less perfect, the bastard child of math. And really what we want to have is, we want to start with the physics, get physical requirements, and we're gonna get some semantics of the physics that it's already clear because we're starting from the physics. And then we have something that we call physical mathematics, which is the part of mathematics that is there to capture and only capture things that are physically interesting. So this is sort of the structure that we want to have, that it's physics first. And again, there are lots of cool things that I could say. I think I have to cut it. But one of the things that is really important is that the physics will always live forever in the informal world, because the physical things, the experiment and so on, they live in the informal world. And when we are mapping them to the formal system, we are making some choices, we're making some approximation and so on. And the objects in the formal parts will look crisper and nicer, but it's because they are approximation of the real world. The real world is actually a lot more complicated. And one of the things that is important to us is that the way that you take things from informal to formal is really let's say 90% of the physics, because once you've set those definitions, everything else is sort of turn the crank. It's all defined, and that's the part that is kind of least studied and least understood. And one of the problems is that we need to be able to choose axiom based on how straightforward are they physically, and not how nice mathematically they are. You know, they follow the latest craze in category theory or whatever. No, we really have to define them from the perspective of the physics. And so just to give you a sort of a high level view, we were talking about Hamiltonian mechanics before. And so the idea is that we are going to have a topological space, which is a space of experimentally distinguishable cases with verifiable statement. We say we are going to add the fact that they can be identified by independent continuous variables, and then you say you know that they are locally isomorphic to Rn, therefore you get a manifold. Infinitesimal reducibility is going to give you the differentiable structure of this thing, because you need to be able to talk about infinitesimal parts. Then observer independent count of states is what gives you ultimately the symplectic structure, and determinism reversible evolution is what's getting the Hamiltonian evolution. So the point is that we need to have these type of things clear in our head to be able to do all this, understand what pieces are we adding whenever we are adding some of these mathematical structure. And so just to give you a very quick idea of how this works, I was saying before that our sort of the building block that we have is the notion of an experimentally verifiable statement. So something like the sky is blue is a verifiable statement because I can look outside and verify that it's blue. And something like the mass of the photon is exactly 0, it's not verifiable because it has infinite precision, and we can't test infinite precision. And so mathematically, the idea is that you have a set of statements, you have a subset of statements, and then in the back of our mind, we know that these verifiable statements have a test, and the test succeeds in finite time if and only if the statement is true. The statement can also fail, but the statement also can never terminate or be undefined. And if you have these objects, what you can show is that you can make a finite conjunction of them. So you can take finitely many statements and you can test them one at a time. And if they all succeed in finite time, then the conjunction is true, the end is true. Therefore, the finite conjunction, the logical end of finitely many verifiable statements is itself a verifiable statement. And if you do the disjunction, however, you need only one test to terminate. So if I terminate on test 3, the fact that I have infinitely many that I'm not even going to touch doesn't really matter. But these has to be at least a countable sequence, because I need to be able to find the statement that is able to terminate. And this structure here, what you get with this finite conjunction and countable disjunction, which is the correct algebra for this verifiable statement, is the algebra that you would have in intuitionist logic. So that's why I was saying there are some things that are connected. And just to, again, give you a sense of how this works, we have this axiom that tells us that we are going to be able to have the countable OR, and we need to provide a justification. Like we need to show that we can actually do it. And so we have a sort of a pseudo proof that we call justification. It's maybe something that could have been considered a proof in the 1700s, but it's not a proof by modern standard. And the idea is that we are going to have these tests, and we're going to have this pseudo algorithm where you initialize n to 1, and you run the first n tests for n seconds. And if one of them succeeds, then you return and you have done. Otherwise, you go and increment n and you repeat. And so the idea is that you're running all the tests at some point at arbitrarily large time. You're going to find the test that terminates, and woohoo, you're good. Of course, this is not really make sure that in the model you are consistent. It's not something that you would do physically, but then again, you are sort of using some of the same ideas. And so all the axioms that we have need to have a justification at this level, so that they have to be physically grounded, so that they're physically grounded, and somebody can look at the book and says, why do I have this axiom? I'm going to look at the justification and say, oh, actually, in my case, this justification does not apply. Then it means that this axiom does not apply, this definition does not apply, and therefore I need something else. At least we can start making those judgments, which we don't do right now. We just use Hilbert spaces, and why it's not clear. And the way that this connects to actual mathematical structure is that the statements that tell us everything about a particular object become the points of the space. The statements that are verifiable become the open set of a topology, and the theoretical statements, the statements that are associated to test, become the Borel set. And then there are a lot of things within topology that can be reinterpreted with these things. And I'm going to skip all the details, but the point is that you get a perfect map between the math and the physics, and a really level also that you're able to argue that phase transitions are topologically isolated, because you can verify that you are in a phase transition, and therefore you can have, it makes sense that you have analytical functions that are discontinuous because you're still topologically continuous. So you can make this level of precision of statements, which is great. Another thing that we can do, which I definitely don't have the time to go through, we have a construction of quantities and numbers from a set of operational idea. The idea that every system that we create is a system of reference, and every reference allows you to identify a before, an after, and an on. So yeah, it's basically a collection of 3 statements. And to have a real numbers, you have to find enough conditions on these references to be able to say, they identify a point on a real line. And we have all these worked out. And the thing that is most interesting is that the thing that is hard to get is the order structure. And once you have the order structure, whether you have real numbers or integer, is actually a very simple difference. And what happens is that when you're going to go to something like Planck scale, these assumptions that you made to get the order structure break down, like they're not tenable anymore. And so it's really the ordering that breaks, and there's not going to be an objective systematic before and after of these references. And therefore, like the real number structure breaks down at a more fundamental level. It's not that you just don't have the real number, you don't have an order structure. And what's going to happen there is part of something that we're still figuring out. Part that we're still working right now is instead of creating a general theory of states and processes, something that, as I said, we can define these things more abstractly, and then have classical mechanics and quantum mechanics be proper specialization of the mathematical framework. And very quickly, we are going to, again, think that the notion of ensemble is the primary one, because if physical theory are to be repeatable, then in a lab we prepare ensembles and we measure ensembles. So that must be the primary object. And also, if the physical law describe a relationship, that are always applicable. Again, they don't describe relationship of one particular thing at a particular time. They say whenever I have something, I can do this other thing. Then it's relationship between ensembles. So again, ensembles are going to have to be the primary objects. And so general physical theory basically is going to tell us that at minimum, the physical theory has to talk about ensembles, and these ensembles are going to have some minimal requirements. And the minimal requirements are the topology that, as we said before, that it connects to experimental verifiability. We need to have a convex structure that represents the mixture. Again, I have two ensembles, A and B, and I mix them as 40%. I get an ensemble that is in between. This is a convex structure. And one of the things that we are working on right now is a generalization of probability that works essentially both in classical mechanics and quantum mechanics. And what you need to relax is that the measure has to be subadditive instead of additive. And the measure really recovers additivity in the classical mechanics and quantum measurement. And I would need at least probably 5 minutes to talk about that, so we'll skip it. And if you guys want, I can go back. And the third set of axioms is basically the axiom of entropy, the fact that every ensemble has to have an entropy well defined, and the entropy has to be strictly concave, and there has to be an upper bound on the increase. And the upper bound on the increase actually allows us to recover orthogonality between subspaces. And the entropic structure, as I was saying before, allows us to recover very quickly a geometry, and we can define these sort of geometrical objects without even knowing that they are where we are in a classical space and a quantum space. In the classical space, for example, this recovers the Fisher-Rao metric, and in the quantum space, it recovers the Bourret metric. So they're very simple things that you can do, simple definitions that make sense, and they allow you to recover the core structure. So wrapping it up, the idea is that with the assumption of physics, we have a different approach to the foundation of physics. We don't want interpretation of theory of everything, but really wanted to have physically meaningful starting point from which we can construct a mathematical structure or recover the laws. We have these two approaches, the reverse physics, where we start from the law and find a physical starting point. The classical mechanics is completed. We are working now to formalize the quantum mechanics. We think we have the right ideas, but they need to be written down to be sure that they are right. And then for the physical mathematics part is instead rederiving the mathematical structure from scratch in an axiomatic way. We are able to get to topology sigma algebra very well. That part is completely done. And now we are in the process of formalizing a general theory for states and processes in terms of ensembles. And of course, the goal is ambitious. And so we are trying to find people and experts in different areas that allows us to sort of make sure that we're going in the right direction. It's a part of this project. I have to be able to talk to mathematician, physicists, computer scientists, philosopher, logicians, which seems to be very different ways that you talk to logicians and other mathematicians and so on. And for people that want to know more, we have a project website where all the papers and presentations are there. We have this open access book, which is really the main focus of where we put all these parts. And one of the problems is that since it's very interdisciplinary, it's very difficult to write papers that are so interdisciplinary. So we first work on the book where we can check everything together, and then we start taking some pieces and publish papers. I have two YouTube channels, one in which I take some of the results from the research for an undergrad audience. And now I also have another research channel. I guess a little bit like you guys have. I do live streaming where it's mostly me talking, and surprisingly, there are people that are following it, which is crazy. And all that I'm doing, as I said before, is on GitHub. So all the papers, the books, the slides for the everything that I go is there. If somebody is interested to go and even just send me spelling corrections, that's also great. So that wraps it up. If you guys want to have questions, we can go through and talk to where you want.
Yeah, well, amazing. Thank you so much, Gabriele, for this. As I said in my email, I was looking forward to this this very topic, this very effort. Is almost like seeing my unrealized dreams from my PhD. So it's definitely great to see that. So yeah, I think we do have some time for questions. I mean, we don't want to keep you longer than you need to be here, but I guess Nick and I both have our pet questions that want to address. So mine is about the symplectic structure, and I'm sure that, but I'm also very interested in the phase space question. So I don't know, should we take those two topics a little bit and discuss it a bit? You think?
Up to you guys. I'm here for you, so you decide.
Well,
You okay with it, Nick?
yeah,
Yeah, go for it.
Okay.
I'm not
So,
going anywhere.
So I'll start with the question on the, because I think it's a bit more, it's a bit smaller of a question, which is this argument. I mean, I'm fascinated by the idea that you can actually conclude that you need a symplectic structure. And let me just preface where I'm coming from very briefly. What kind of information I have loaded up in memory to say this. So in my work, which is, by the way, it's you can find online. It's very accessible. It's not like super technical. It's written to be kind of in this pedagogical style of like explaining and so on. So I feel very sympathetically towards your efforts. I've kind of been there, and I know what it feels like. So, but anyway, so one of the things that I was trying to learn in this work was I was trying to get a sense of why Hamiltonian, why symplectic, right? Why this specific structure. And I have to say that after my exploration, I didn't end up with a conclusive answer of like, oh yeah, symplectic because of this, right? Like in this I did have that intuition for other aspects, as we said, like the infinitesimal reducibility about continuity and smoothness and all that stuff, and even certain properties of your spaces like compactness and non-compactness and things like that. Like I could even relate those to other physical meanings, but specifically the structure being symplectic, I couldn't really pinpoint, and so I did my best at kind of cataloging many different structures and specifically noting what the parallels were between classical dynamics and quantum dynamics. And I'm using dynamics in a very deliberate sense here because I didn't want to say classical physics or classical mechanics and quantum mechanics, because when you look at quantum dynamics and you think that all you need is Schrodinger's equation, and that's basically what leads to everything else, right? It turns out that Schrodinger's equation and just classical mechanics in some cotangent bundle of some configuration space, they are exactly the same equation. Like for a Poisson geometer like me at the time, I could not see through it. And so I was trying to kind of disentangle why one was quantum and why the other was classical, kind of playing this game of blinders where I was not allowed to look at, the interpretation is that your states are actually pure states of this. Like I was just not allowed to do that. I was just trying to look at the pure differential geometry of phase spaces. So one of the things that I noticed is that both of these cases, classical and quantum, correspond to two cases in which you begin with a what I call the primer state. Primer state. What am I saying? Yes, primer space of states. Sorry. So it's a first manifold, technically speaking, from which you are going to canonically define a Poisson manifold, right? Or a phase space with a symplectic structure, but more specifically. So in the case of a classical state, a classical system, you would get a configuration space. So in most applications, this is going to be something like a smooth manifold that is generally non-compact, but could be compact, and has often a metric, a Riemannian metric, right? I mean, classical example is Euclidean space for Newtonian mechanics and so on. But also any configuration space of Lagrangian mechanics works, right? And so from that point on, you realize that, yes, you have a direct path into a symplectic land by taking the cotangent bundle and blah, 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 and that's it. So in the quantum case, you take your primer state space as something that encapsulates, say, the superposition principle that you observe directly in experiment, right? Like you take your experimentation and you say, okay, so I have something like a Hilbert space here. It doesn't have to be Hilbert in some technical sense. It can just be some, complex valued or real valued. It doesn't matter. The point is you have that space, and the empirical properties that you attribute to the space, which essentially are captured by this Hermitian form in your space, automatically take you to this construction of the projective Hilbert space or projective space there, and that is canonically a symplectic manifold. And so these two constructions are so different geometrically, right? Like cotangent bundle construction means this conjugate variables, blah, 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 this idea of velocity, right? Of like velocity being your second independent state and so on. And the other just corresponds to doing some global operation on your space. When you take a ray, you basically are saying, hey, I can grasp my whole space in my hands and just define a equivalence class of such things, and I have this projective space, and there is where you find your Hamiltonian dynamics. And so once you get to that level, both are just Hamilton's equation. There's no distinction between the two. So I find it very interesting because on the, you know, when you do the projection construction, the projective space construction in the quantum side, you lose all sense of the canonical separation. So you no longer have anything like a fibration or a bundle or anything like that. It's just a manifold of its own. Any sense of what is a variable and its conjugate is kind of a local construction that doesn't really bear any global structure. However, in the cotangent bundle, you do have a canonical way to distinguish what is a momentum direction and what is a position direction, right? Just by definition. So I was trying to come up with all these considerations to see what is the difference between these two, right? And so I kept on going on. Yeah, it might be the fact that you don't constrain your variables in the case of velocities, like you can assume that things are unbounded, and like, but I was never really fully satisfied. So going back to your point that I mean, this wasn't me axiomatizing a symplectic structure. This was me saying, I want data that is physically meaningful, from which mathematically one can uniquely arrive at a Hamiltonian system, right? So my question is then, how can you actually constrain all the way down to symplectic? Because there are many aspects of Hamiltonian evolution that are sufficient for, say, something like Schrodinger's equation that don't require exactly symplectic, right? It could be, you could have just Poisson that is not symplectic. You could have compact or quasi-symplectic and things like that are not exactly symplectic, but they're still recovering a lot of the dynamical aspects of it. You know, you have quote unquote Hamilton equations you are retained, but your form is not technically a symplectic form. So, for example, it might not define a global volume or things like that, right? So I'm very curious to know, like, exactly how you arrive at that, because in the classical case, yes, this definition of conjugate variables makes sense. I have a sub question there, which is why only pairs of conjugate variables and not triples, and not like, why not define like families of conjugates that just cancel with each other, you know? So anyway, so those are my two questions. First, how do you actually constrain it down to exactly symplectic in this technical mathematical sense? And the other is, if that argument works, why doesn't it work to aggregate more conjugates in the same family so that they are all kind of in an ensemble of conjugates, all balanced, right?
Yeah. Okay, so plenty of things. So the whole problem of classical and quantum are the same but not quite different. That's something that I'm still circling around. And I do think that looking at the space of ensembles instead of the space of pure states on one side or the other makes things a lot easier. But let's just go through classical mechanics. Okay, so let's see. We have the symplectic form. Okay, so what is the symplectic form? It's something that you give it two vectors and it gives you a number. Okay, so the first thing that you need to tell me is, what is that number? And
say it again. What is what?
The first thing that you have to tell me is what physically that number is. Like, what does it represent? Okay. And so this is again where it is a lot easier if you say, okay, let's do the 1 degree of freedom first. And you say, okay, I have a symplectic form. I am a single degree of freedom. I have two elements. And I say, okay, what is it telling me? It's the volume. In the 1 degree of freedom case, the symplectic form is a volume form.
Yeah, the area form.
Yeah, a volume in the space.
Yeah, so, volume. Yeah.
Okay, so it's telling you that's volume, and we know from statistical mechanics, the volume is in position and momentum is the count of states. And it only works in position and momentum. If you use the position and velocity, you do not get the count of states. Okay? Because position and velocity, the way they change, right, they both change contravariantly. So if you make a change of coordinates, the product between dq and dx and dv is going to increase numerically. It's not an invariant.
Mhm.
Okay? So
Yeah.
in 1 degree of freedom, you can say, okay, what the symplectic form is doing is just giving me a volume of these two variables, and the volume is a coordinate invariant. Meaning, coordinate where I mean, if I change the q, changing the q induces a change in the p such that the volume remains the same.
Yeah, I mean,
okay, so
all right, but I think right, but this is okay. So
I'm
maybe
just going one
continue.
direction right now, right? So I'm taking the math, analyzing it, and then telling you, from the math what I can get, and then the problem is going to see, can we go back? Okay, but in principle, the idea is that we have this manifold. We have position and momentum. These position and momentums are two variables, but they're linked in the sense that if I change the unit of one, I change the unit of the other, and the volume remains the same. And then you ask, and you say, physically, this represents the count of state. And then you say, is it physically relevant, the fact that the count of state does not change if I change the units of Q? Well, yes, because if I didn't have a count of state that was objective, I wouldn't have an entropy that was objective. I wouldn't be able to talk about these things in an objective way. So yes, the count of state has to be unit independent with respect of the Q and the P. And the question is, well, if you can go on the other side, saying that if we want to have an objective count of states, then I need to have one Q and one P, then we are at least done it for 1 degree of freedom. And then you argue like this. Suppose that you have a manifold, right? And you have the whole units of all the variables is defined by only one unit. And I call that only one variable, and I call unit the variable Q. So the Q is the thing that defines the unit. And I'm going to have a bunch of other variables that I don't know how many they are, but I know that things are dependent on that. If I make a unit transformation, I change one unit, that's it. And then I need the volume of this thing to be invariant under Q. If I make a unit transformation, a Q hat as a function of Q, I'm going to change everything, but the volume has to be the same.
Sure.
Okay?
Yeah.
And then you say, well, if I only had the one variable, I would have a problem. Because now the change of Q is really changing me the volume. There would be one particular coordinate system in which the volume would be, exactly the measure of Q. So that doesn't work. Now suppose that you have two or more. Well, if I have two or more, I change the Q. I know that the volume is constrained, right? So I have one constraint for the volume. I have one choice for the Q. It's not enough to fully determine the change of the other two variables, because I could still change, make another change between the two variables that does not change the Q and does not change the volume. So it wouldn't be true that the Q by itself defined the unit system.
Mm-hmm.
So the only way that I have is that for each Q, I have another variable, only one variable. And then since the volume has to be coordinate invariant, a change of Q has to be compensated of a change of P.
Right.
And then you find that the change of P has to only be a function of Q. And then you find the P therefore has to be a change like a covector essentially.
Right. But I mean, I see how that works, but really what you need is that a changing a rescaling of Q determines the rescaling of any conjugate variables that would be grouped with Q. it doesn't matter. It's only one, right? Because you could. I mean, and this is getting into a bit of.
No. Okay. So let's say that you have a Q and just rescale these two, but then you can still make a coordinate unit transformation.
No. That's not what I mean. What I mean is that you could have a Q and then a P and a P prime, say, right? Like that are paired to Q. The point is that when you group Q, Q, P, and P prime all together in some volume state space, that thing is unitary, right? So really it would work if you had a 3 form instead of a 2 form, right?
But Q wouldn't be the only thing that defines the unit, because now you can change your P and P prime without changing Q. So you change the units of P and P prime, and then it's no longer true that Q is the only variable that defines.
No, you could not, because in any of the three, they are in triality, right? In this sense, they are fully constrained. So the change in one fully determines the other three exactly in the same way. So this is basically defining a 3 volume form instead. So this only works for this is why I had my first question about one parameter, 1 degree of freedom systems, because it's very obvious here for the surface case, the surface area case, that all right, I have 2, but if you actually go into something that, I mean, it's still 1 degree of freedom, but instead of saying I'm going to land in an area form, I want to land in a volume form, in a 3 volume form, in a 3 area form, right? You have the same argument, because
okay, fix the first, right? Now you're going to have an area, right? And so you're going to have a surface where it's spanned by the other 2 variables.
Yeah.
You can make a change of one of these 2 variables such that the volume form remains the same, and therefore you haven't changed the Q.
No, I mean, but by that argument, you would say that if you have an area, then you fix when you have a line, and you can still change along the line, right? So that doesn't really work for that. So my point is, I mean, this point is going into some exotic territory, because it's proposing that in principle you could justify Nambu-Poisson structures, and not only Poisson structures, which are multi-ary brackets.
I think you understood the argument. That's the problem. Like you have 2 freedoms. You have the freedom. You have 2 constraints. One, the constraint that you put when you change the Q, and the other one is the constraint that the volume form has to be fixed.
Yeah.
And you have only those 2.
Sure. And I'm saying that what I'm saying, those 2 are met.
Yeah, but you're adding some other way to change the relationship between the variables.
Not really, because that's like saying, well, you define things with momenta because they are conjugate variables in the canonical construction of the cotangent bundle, right? That's why they are preserved. Because
no, they're preserved because I change the unit of one, the unit of the other is fully determined. There is no other choice that I can make in the unit system.
Correct. But that's what I'm saying. That is the same thing. Saying that you construct the cotangent. I mean, the cotangent bundle is a dual space, right? Pointwise.
Okay. Look, if you have a volume form in 3 space, right?
Yeah.
You're going to be able to sort of let's say diagonalize, find the 3 vectors that are orthogonal to each other.
Well, we don't have a sense of orthogonality. There's no metric, so there's no sense of orthogonality.
There should be a sense of linear independence. There you go.
Sure.
I only care about linear independence.
Sure. Yeah.
Okay. So I know these 3 things are linear independent.
Sure.
And therefore, this one is linear independent from these 2.
Yeah.
Okay. So I'm saying that if the Q changes, right?
Yeah.
There is only one way for the other variable to change, and that's it.
Fine.
Okay.
Yeah.
Now it's no longer true if I have 3, because I keep these fixed.
Yeah.
And I can change these 2.
But the argument is not geometric. It's not about the thing being a 3 form in 3 space. The argument is that the reason why you can rescale a Q and you can compensate with a P. Yeah. I mean, these are not just real variables. P is the component of the cotangent space of the tangent space at Q, at the point Q, right?
Yeah, I have a, like, what I get is just a symplectic manifold. I don't get a cotangent bundle of anything. I just get a symplectic manifold.
wait. So, no. So, okay.
The sphere is a symplectic manifold, and it's not the cotangent bundle of anything.
Correct.
And it's something that I want to have. So I get a symplectic manifold, not a cotangent bundle.
Okay, but then, right. But then that would apply to quantum, not equally, right?
That's why you have the block sphere. That's why, you know, the two-state system is a sphere, so that it's symplectic.
Okay, so what I'm trying to say here is so the construction, okay, so if you want to argue with this principle of you want to preserve the unit area when rescaling, right? And
it's more than that. It's more than that.
I understand. I understand it's
Okay.
more. I understand it's more than that. But if you want to get that in particular,
yes,
right? So there is more, and you can tell me why the construction will fail. But the reason why you can induce, so if you tell me that you just have area and you have two dimensions, right? Two independent dimensions, then what you're telling me is that sure, that areas are two-dimensional, and if I have one dimension, I constrain fully the remaining one when I fix the area. Okay. Yeah. But I think the argument is much more subtle than that, because what you actually are saying is that if you have a rescaling transformation of one of your variables that actually should be a full diffeomorphism, but that's a different point, that you are inducing a compensating transformation on the conjugate variables, right? And that happens with this canonical construction that is completely devoid of dimensionality. It doesn't matter that we are in one parameter degree of freedom or anything. It just says that, okay, if this variable was defined to be conjugate to this one from a algebraic point of view, it is kind of the same as saying that it's going to compensate because it's dual, right? Like that's what it means to add these extra dimensions, right? Because they are not just dimensions, they are these dual constructions, right? That locally work. And you have this that can work in any locally symplectic space, right? Like this you can always do locally. So my point is, I'm only poking, I'm not finding the argument invalid. What I'm saying is I'm poking at a possible avenue for more constraints to be added to make the argument work, which would be to constrain somehow that we really want only one conjugate partner to a given variable.
I told you, Carlos, the way that I think I prove it and other people agree is the constraint is that the Q fully defines the unit system.
And that's still true in the system I'm telling you.
No, it's not.
Yeah, because the thing is, people
repeat
normally
to me the argument that I'm making and see if you get it, because I don't think you get it. So
no.
Why I think it works. Repeat my argument.
Well, because you're saying that you have, in the case of three variables, in the case of going three-dimensional, if I made a change in the Q, I could, and I wanted to preserve the unit volume in that case, right? There will be possible changes of the P and P primes that I could make that would still keep the volume fixed, right? That will be independent of the change of the Q, right? That's the argument, isn't it?
And then what happens is that it's wrong. Why can't I do that?
Well, because I can change the P and P prime independently, and you know their units are not in correlation with the change I made in Q, right?
Okay, so why don't you?
So what I'm saying is that you can construct something like a trio of conjugates, right, that are canonically grouped together in such a way that any of the three constrains fully the changes in the others. This is not an argument about them being three-dimensional. I'm not using the fact that there are three independent dimensions in any space. I'm just saying that canonically I can construct such a thing. It's called a triality, right? I can impose a triality on, it's not really a triality, it's fully antisymmetric triality, whatever, but it is just a multilinear imposition on these things, which is very analogous to a symplectic form, but it's ternary. It's rank 3 instead of, or arity 3 instead of 2. And
so to define that, you're defining some constraints of the choice of variables, right? In the same way that defining a unit defines a constraint of the choice of variables.
No, not really, because you're not, you're just saying, you give me your Q, that is your unique unit defining variable, and then I canonically construct the P's associated to it. And when you change the Q,
how many ways can you do it?
Uniquely, for any given number of P's.
For a particular choice of technique of how you do it.
Well, I mean, it's completely independent. I mean, it is canonical in the same way that you construct the cotangent bundle, right? Like you give me.
I don't construct the cotangent bundle. I don't do any construction.
I know that you don't do it explicitly, but it is equivalent mathematically because the cotangent bundle is the unique vector space that has the property that you want, which is that when you have the dual pairing, which is the application to each other, you preserve the quantity, which is essentially what you're saying, that you want the scaling to be compensating. So what I'm saying is that there are constructions in multilinear algebra that I'm not saying it's wrong. What I'm saying is that there are constructions that have the property.
I don't follow. So are you saying that the argument that I'm making does not work or works?
No. What I'm saying is that the argument that you're making,
yes,
only constrains that you need to define uniquely group correlates or conjugates, but it doesn't constrain to the fact that it has to be another one. It is very exotic to consider more. There's very little literature. That's why no one thinks of it, because there's almost no literature on like ternary symplectic structures. Those things are very far in between. Some literature exists, but it's very, very exotic. But what I'm saying is that property is the right one, but it doesn't actually constrain to pairs.
Let me understand, because I don't understand. So it is true that this ternary structure would be a volume form or not?
It is true it will be a volume form.
Okay, so if it's a volume form, right, and I'm just in the linear space, so I just think this is a matrix, right, I'm going to be able to change the base vector of the matrix. So therefore, when I pick one direction, picking one direction and therefore one unit, rescaling one size, it does not tell me how I'm rescaling the other two.
But you will destroy the structure if you do that. You destroy the geometric structure.
You're working on the other. So I start with the physical thing that I want to justify the structure. It's not that somebody gave me the structure.
I know.
And I can't break it, right?
I know. But that's what. But if the point here is that you want to constrain from the physical argument,
right?
That you actually only want a partner, a conjugate partner, and not a conjugate trio, right? Then you need to find some other argument. It could be just Occam's razor of saying, I don't want multiplicities when there shouldn't be, right? But you need some extra bit of information, because if all you want is a mathematical structure that when you change one, all the partners changing defines a volume form and all change in consonance.
You're just repeating me the same thing, and you're not addressing the questions. Like either the argument that I have works or it doesn't work. So if it works, I'm already constraining the fact that those ternary structures are be excluded, because I am, by saying, look, the whole structure has to be fixed by a single variable, right? So either that works or it doesn't work. If it works, then I don't need I'm already showing that I can't have those ternary structure. If it doesn't work, there is an error in my argument, and then you have to tell me where the argument goes wrong. And I still don't see where it goes wrong.
So the argument is not wrong, because what you conclude is that you should have a structure in where the change of scaling of one variable determines the change of scaling of the others uniquely, so that the volume form is preserved, right?
No. I'm saying that the rescaling of one side while fixing the volume fixes the rescaling of the other.
Okay, which is, I understand the same thing I said, but yes, I understand that you fix the volume, you change the scaling of one, and then all the changes of the others follow through uniquely, right?
Yeah.
So that property is true in higher RET constructions of volume forms.
But again, I would be able to make that same change by rescaling the other two parts in different ways. So it is not true that the rescaling of one and the conservation of the other, and I don't understand. Like I don't see, like, point by point the argument. I don't see where.
Well, because these are not just numbers, right? Like they are not constrained to be numbers. They are.
Mine are constrained to be numbers. I mean, I'm talking about the real valued quantities. Is that the problem?
No. The problem is that, I mean, they have transformational properties, right? They are numbers with transformational properties. I mean, you are addressing a transformational property to make the argument, which is to say, when such and such transformation happens in here, I mean, you're saying rescaling, but really, as a form, it's just any multilinear transformation should keep the thing, when you constrain the whole thing to be invariant, should determine all the others. That's not true in general, right? Of course. But you're saying that your argument, and it's a correct argument to say, but I actually want it to be, I want a form that if I fix its value and I change one of the entries, I want the change in the remaining one to be fully determined, right?
Mm-hmm.
That's great. It works fine. I'm not saying that argument is wrong, but what I'm saying is that the arity of that map, of that tensor that you have.
If you're saying that the arity is not fixed, then you have to say that my argument is wrong. That's
okay, but then I say your argument is wrong, but I don't think it's fully wrong. I just think that the structure that is available to fill the role of that thing, which is what we call a symplectic form, is the binary case of that. But you have higher arity symplectic analogs that would fit that role. I don't know what this means. I'm not saying, oh yeah, you're clearly missing one avenue that you're not considering. I'm just saying that argument alone is not sufficient to constrain the arity of the form.
Right. Then you're saying that the argument is wrong because I'm saying that it is sufficient.
But then maybe I'm not getting your constraint, because to me the constraint seems that, and we broke it down quite clearly, right? Like you want something that is a form that's multilinear, that once you fix its value and you only want to transform one of the arguments, you want the other arguments to transform in a unique specified way so that everything preserves the value.
Right. So
that is a property that can.
I have these, I have these three vectors, right? I'm going to change the rescaling. I'm going to rescale one. I'm saying that the volume is conserved. If I have three, I could rescale this one and keep this unchanged, or I could rescale this one and keep this unchanged.
Absolutely.
Therefore, if I have three, it's not, I don't have enough constraint. If I have two, whenever I'm rescaling this, so this is going to shrink and I'm good.
Fully. So just as volumes in space, that's totally true. But that's not the mathematical structure that we're considering here, right? We're considering forms on vectors, because that's what the symplectic form is, right? So you're constraining the domain of mathematic objects that we are constraining.
I'm still trying to understand what is it that I'm missing. I still don't understand.
So the point,
a form is just a linear function of vectors.
Correct.
Okay, so it's just like if I'm in the linear space and the vector space, it's just a matrix to me.
Okay, a matrix. Okay, but that here might be the problem. It's a matrix. It's represented by a matrix, but it's much more than just one matrix. It's an infinite class of equivalent matrices under all the linear transformations of a matrix. That's what a form is.
What do you mean by that?
Okay, so maybe this was the problem. So, so a form is not a matrix. I mean, just let's get it out of the gate. So a matrix.
Tell me why it's not a matrix.
Okay, so a form is a mapping from vectors, a multilinear mapping from vectors to whatever you want, like scalar or something, like a volume form.
In this case, it's a scalar, right? So it's
a scalar, sure. Yeah. So let's say that we have volume form. So it's a multilinear map from vectors to scalars. Yeah. So if you choose a basis of your space, that becomes a matrix. Absolutely.
Yes.
Right. So, but choosing a basis is kind of choosing a gauge, right? Like it's completely irrelevant.
Choosing a basis in physics means choosing a unit. That's kind of the whole point.
Well, but okay, sure.
I mean, in the same argument, a vector isn't a list of real quantities. It's a
right.
The vector in space, and you use a basis to express it as a scalar sum.
Yeah. So I understand that choosing a basis is choosing a unit. Totally agree. But now you want full transformations of units, right? You want to be unit independent, right? You want to be observer independent. This is what this transformational property now here means. So in a sense, a form is the physical thing because it's independent of basis expression. A matrix is the observer dependent expression of a form. Let's put it in this sense, right? Because it's dependent on a specific choice of units. So when you're thinking of the mathematical objects that you want to range over to constraint in an argument like, let's speak out why is it a symplectic form and not other kinds of forms, then you are in this realm of, okay, all the possible forms, let's say that I could have in this vector space of states that I've defined, right? So the constraint that you're saying is that I want, as you described it, is I want a form that once I input one of the arguments and I have a fixed value for it, for the remaining ones, I want that if I transform that first argument, that all the others transform in a uniquely determined way so that the value of the form doesn't change, right? That's the behavior that we want out of it. What I'm saying is that traditionally, that is exactly what
Oh, wait. No, not only the form changes, but also the other arguments that are putting in.
Not the form. I'm saying the value of the form is unchanged, and you want that the values that you would enter in the other arguments, the vectors that you would input in your form, they change accordingly in a uniquely determined way.
Right. So the plan is that. So it's feeling like this. I have Q and P, which I can think of vectors, right? Let's call it K. So we don't even call it P because we don't know what it is. So we have a Q and we have a K, which are two vectors. I give it to the former, which gives me a number. Q has a certain unit, and Q, I don't know what the unit is.
Sure.
Okay. So there might be multiple units.
So when you transform Q, this means in this more sort of a pedestrian language, you would apply some linear transformation to it.
I do a Q hat equals a Q hat of Q. So now I go from Q to Q hat. I change.
Yes, and doing that means that you apply a linear transformation to it, right?
In the simplest case, yes.
Well, not in the simplest, but in this case, in all of them, because you're only defining forms on vectors, right? So you're not really allowed to do anything else.
Well, at some point later, I will want the Q to be nonlinear. So yeah, no.
Okay, but fine, but then you will be in the realm of the geometry instead of just the forms. Exactly. But so the point is, okay, so when you transform Q,
I go from Q to Q hat, and I want to say then if I go from Q to Q hat, there's going to be an induced transformation from K to K hat, then K2 to K hat 2, like a whole induced transformation of these things that is unique, and there is no other freedom to do it.
So that unique transformation, if you have a transformation that applies to Q.
By the way, this was a short question, right?
Yeah, I mean, but because I thought it was just a clarification. But I mean, it seems that there's something to clarify here, like deeper. And so the point is, in that Q that you transform, if that is transformed under some linear transformation, at least infinitesimally, which is the point, then the linear transformation that you should transform the other thing, call it K or whatever, is fully determined by take your symplectic form, whatever you're trying to find, and you will find that it has to be the inverse matrix, maybe conjugate with this matrix that you're transforming your Q with. In any case, it's fully determined by it, right? And so the point is that in a case with 3, if I gave you, there's Q and there's now K1 and K2.
I gave you a Q hat.
Yes, and you make a Q hat that is a linear transformation, right? And then I tell you, well, this K1 is going to be transformed under this thing, and I'm going to do it as a cubic root of your, instead of a square root, you're going to do it as the cubic root of your main Q, and then you're going to transform the other one with the minus 2/3 root of the thing, so in such a way that the total linear transformation is actually the identity for the form that the form sees. So that preserves the value of the form, are linear transformations, and they are fully determined by a single linear transformation on the Q. Therefore, the properties are retained. The properties that you want are retained.
And again, to me, no, because I can still make a transformation on just the Q1, the K1 and the K2 that leave the volume unchanged and doesn't change the Q. I can still do that.
No, because I mean any non-zero transformation will change the form, will change the volume. Like if you only do a transformation in one and you completely forget the others, unless it's 0, it's always going to change the form.
I don't understand. It's a linear space.
It is.
Okay.
So if you rescale one dimension without doing any other rescaling, it's always going to change.
I fix the Q, as I keep saying, I fix the Q, I rescale the K1, so Q remains Q. K hat 1, K1 goes to K hat 1 equals A K1. And K2 goes to K hat 2 equals 1 over A K2.
Yeah, but that's the thing is that's not an allowed transformation of
that.
that.
It's not allowed. Of course, it's allowed. I can change it. I can change the numbers. Of course, it's allowed.
No, of course, but the point is that is your form will not be linear in that case because you're. I mean, so your form will not have a linear in the sense that it will not have a form expression because it will depend on what basis you're writing it effectively, because that would mean that you
again I still don't understand.
Okay, so maybe yeah. I mean it is
no, because I want to understand whether they're missing something. If I'm missing something, I should know, and I still don't understand. So I have three vectors, and I have a linear function of three vectors in a specific choice of variable.
Yes.
That thing for that specific choice of variable is a matrix.
It's a three index matrix. Yes.
Eh?
Three indexed matrix. Yeah.
Yeah, it's gonna be fully antisymmetric, so it's gonna be 0, 1, -1 with the other one. It's the usual thing.
Well, it doesn't have to be, but yeah, it will be fully antisymmetric.
Well, I will be able to pick a set of coordinates therefore a choice of units for which that is going to be in that form. Certainly. I mean, the canonical units are those that put the symplectic form in that particular way. So I'm going to be able to do it with any volume form. I'm also able to put it so I find the three things, right? And I say, so if I choose Q, if I choose one variable, I'm going to be able to find the other three such that I have this canonical structure such that the volume form is 0 in the diagonal, +1, -1, +1, -1, 1, -1. I can always do that. So I can pick my unit and I find two conjugates such that the volume has a nice form. Okay, and then I keep the Q, right? And I'm gonna make a change on these two, right? I'm gonna multiply this by A and divide this by A.
Yeah.
I made a change of coordinates. I've made a change of units without changing Q. That leaves the volume the same. Therefore, it's not true that once I pick the first component, the first unit, all the other units are fixed because I can always make a different choice of units.
But
that's the
yes,
argument.
Because again, that's relying on the fact that you want to perform independent transformations that basically forget where the form came from. And in that sense, the argument works. That's why I said I never said the argument doesn't work. So the argument works if you're saying, okay, I just want to narrow down what spaces I can have where I only have this. I can only have this property of for the one transformation fully defines the other. Because in this case, you would always have trios of transformations, and the theory for those is richer. It's not unique. It's not a single one, but it's a family of transformations that binds the property. So that's why I was qualifying that if what you want is the uniqueness of the property.
The way that I would requalify that is those constraints that you're putting are constraints on the units that are exactly the argument that tells you that you shouldn't have, because that constraint on those other units corresponds to a choice of unit system that is independent of the choice of Q.
Okay, I think I see. So I think I see where the distinction is, because if you want to treat your dimensions as fully equal, right? As you said, you're not constructing.
The real numbers come from the topology, right? And the topology is going to tell me, look, I can measure. It's the product topology between the two real numbers. So
right.
On that ground, I'm going to be able to say I can measure one independently from the other, and therefore that there are not going to be any constraint that forces me that. And then I add the constraint of the units, and then I get a unit system. But before talking about units, I can do whatever I want.
So I think yeah. So I think I understood that was the case. I was just trying to push the that if you wanted
I
something
appreciate it. So the fact that I get a little bit argumentative is just because I'm Italian, not because
no,
I
absolutely. I don't take it. I mean, I appreciate it a lot. So I mean, I think
Okay,
because I wanted to understand as well. So anyway, I think I fully understand where we are now. So I'm sorry. I'm gonna let Nick go ahead. And but thanks a lot, because I actually understood much better what you meant now.
Yeah, I think I understand like something that I never like heard of, like these type of constructions. But yeah, so but I was sure that at some point. Anyway, yes, go next one. That's
Wow.
it's a bit late.
After such heated discussion, I don't know even if I should go next or not. Well, my pet question was about like those ensembles. That's what we can clarify next. Maybe I'm just using terminology wrong, but just as scholars, I can maybe preface it a little bit where I'm coming from, right? Because I'm mostly not going from mathematics, but something like computer science,
Yeah.
and we do a lot of it like life science things with actually coding in Wolfram language. So I guess maybe that's like the best way of prefacing it, actually showing what I mean when I do probability distributions and so, right? I think I just gonna show you some stuff.
Yeah, it would be nice to have a board to be able to this discussion. I think we would have gone through the solution a lot faster.
Yeah, it's like you can draw on my screen if you want to clarify it. But like first of all, it's like when I say that we have like some quantum state, right, which is some kind of block vector on your block sphere, right? This is the quantum state. What we usually think of it as just some kind of complex amplitudes, right, and some bases, right? When I say that you can transform it to the probability distribution, it literally means you take it the
Okay,
density
so let's get that. So that's a mixed state, right? Because it's inside.
No,
the
that's a
state.
pure state.
Ah, no, okay, it's a pure state. Okay, it
Okay.
looked like it was inside. Okay, good. So this is a pure state.
Yeah, that's all. We take a pure state. What I say when we can transform it to a probability distribution, density matrix has 3 degrees of freedom. Well, for arbitrary state, for the mixed, for the pure state it has 2, right? You can literally like turn it into a vector of sorts, flatten it out. It's like called vectorization sometimes in literature, right? And just choose some kind of basis that you transform the whole vector into some beta vector that looks exactly like a probability distribution. That's what I mean. It's just a basis transformation of this vectorized density matrix.
Right, but what you're basically doing there mathematically is, since you have a three-dimensional space, right? You can always represent a three-dimensional point, a point in a three-dimensional space as a convex, an affine combination of 4 points, and you can always do that. And if those points are outside, such that the what's it called, the triangular pyramid, it has the space all inside, then your sum is going to be positive, always positive, non-negative elements. If it's inside, you're going to get also negative elements. That's it. But it's a geometrical thing. It's not really a physical thing. That distribution is not really I can say an objective physical distribution that you can talk like that if you were a classical distribution.
That's why I try to understand why you can't really do it. It's like in a way it's a distribution because you can't think of those, because the projection is the problem here. That when you usually measure the qubit, we assume that there's an observable that acts as a projection, right? And so that you have to actually pick an axis, not the orientation of your tetrahedron that you inscribe your Borg sphere in, but you actually have to pick an axis first, which is your observable, project to it, and that corresponds to your probability that you observe in the real life experiment, right?
Right, yeah.
But why can't we describe the quantum state itself as a probability distribution that just like has this lower bound, right? It only lies inside of the sphere, right? We can pick we can pick an orientation of this probability space, right? We can pick the basis of this orientation of a tetrahedron and just make this mathematical procedure, converting those quantum amplitudes and density matrix to probability vector, and from that point on describe any quantum process as just manipulating this probability distribution,
Right.
even the measurement itself.
So you can do all the calculations that you want in that. As I was saying before, in quantum optics, Wigner function, CV function, all these things, or probability distribution in phase space, they're very useful, and you can do a lot of things.
But
But
what they are
you
not
can't
physical.
think them as a classical probability distribution. It doesn't work.
Why?
Okay,
That's the question.
in phase space, for example, is simply just because when you're making that choice, for example, you're picking a particular ordering for between operators to be when you do the expectation value. So you are in phase space, your Q and your P, you put your Wigner function, you take the expectation of, I don't know, P square times X, right? You're making an expectation of something that is a product of P and Q. You're going to get one value. Well, that value that you get is calculated in a particular ordering of P and Q. It's the ordering where essentially the one that is fully symmetric.
Well, that's you already like assumes a lot of like Hilbert space background that you have dealing with operators, right? Just maybe what I find like difficult is to go to this mechanical analogy immediately. Just keep this discussion like in the finite dimension of Hilbert space, when instead of momentum and position,
I'm not very familiar with this type of construction in these spaces. That's why I go to the other one. It's a lot easier for me to tell you what's going wrong. Here, the similar thing is going to be when you're trying to create products of observables. You're going to have to choose an ordering, and I don't know exactly how it works with. On a qubit, because a qubit is kind of degenerate because you have very few operators. I mean, yeah, you have the commutator between say the different axes, and something is gonna go wrong when you try to calculate those commutators. I mean, you need to understand how to decode it, and I can't tell you what the problem is.
It's like I know that given the probabilities in this basis, I can compute all the probabilities for any observable because it's just one-to-one mapping, right?
Right. So so one thing that you can already see in the diagram, right? The points that you are mixing are not states, right? So the vertices of that thing, right, are not quantum states.
No, they're not.
Okay. So when you are in a classical probability space, all possible convex combinations are states. So you can have expectation value of all those things. But
we're not talking about like strictly classical space. We want to talk about classical space with that lower bound of uncertainty, right?
Right, but that is kind of the problem, is that the standard probability that you would construct like this wouldn't know about those bounds. And so it's going to give you some results that it can tell you all the results. Like you have to put in other results.
Like, what do you mean put in other results?
So let's say that you wanted to calculate the minimum uncertainty that you can have in those distributions. Okay. Well, clearly, if you don't know how exactly the sphere is embedded into the tetrahedron, you're not going to be able to do it.
But we kind of know it. It's like maybe for qubit, we just that's our structure. We just say that okay, that's the maximum symmetric thing that you can embed into tetrahedron. It maybe because it's an equivalent space, right? You basically say
what I'm saying is that you say any point that is inside there, right? You say it's a probability distribution on those four elements, right?
Yeah.
Now I think that this is an even better way. Okay, so let's see. The observables that you can have in quantum mechanics, right? They're always only defined by 2 points, right? 2 points and 2 values.
Well, classical projective observables, but you can have more generalized measurements that like don't necessarily have 2 points, they can have 4. Like we have this measurement operator in quantum information. There are some like, for example, for this tetrahedron basis, there's a special POVM measurement that you can make on your state to get distribution over 4 values instead of 2. And that's the same numbers as this distribution.
Right, but
That
those
the
4 values
information
are not going to be, they're not going to be independent. Like you're not going to be able to assign whatever 4 values that you want there and get all the probability distribution that you want. Because it's going to be constrained. I mean,
well, what do you mean constraint in that case? It is constrained. The distribution's constrained in the sense that you don't have any distribution, right? Because you're constraining to a ball. Again, what do you mean constrained? Again, in this case.
I don't know that I'm going to be able to tell you. It's just that if you were able to put a classical, a quantum space inside a classical probability distribution and just use classical mechanics, you wouldn't have Bell's theorem. You wouldn't have, you know.
Yeah. I understand that. Yeah, because that's not the only constraint that this like construction have. It's not just about the space and this lower bound. It's also about the operations that you can do.
Right.
And, right. Because the operations that you can do have to preserve the information, as you said, right? And you can't do purely probabilistic stuff on a probability distribution that preserves that distribution, because you can't, as you said, refine your ensemble and preserve information simultaneously in a purely classical way. Like you can't discard things, you can't add information, and you have to perform some kind of rotation that preserves the distance from the center of the block sphere. That's what hard to do classically, right? That's the constraint, additional constraint on the operation and the quantum process that you have.
Right. So that's kind of what I was hinting before, is that the way that you could compute so if you have a 4-state space, classical space like that, you're going to be able to define the Shannon entropy of those things. Right?
Yes.
You have that distribution. You can calculate the Shannon entropy. The Shannon entropy of that thing will have nothing to do with the polynomial entropy.
I agree. It's like we discussed it like yesterday. We like had a whole lot. This is like the space of entropy on that particular picture, right? It's for, you can even define it for lower dimensional space. So it's distributed in some weird way. So it's not, it doesn't correspond to the von Neumann entropy, but it's still kind of convex and bounded from both. It's still bounded from below and from above.
Right, but the point is that when you have that definition of entropy, you assume that you have a full classical probability space.
Yeah.
So you're basically taking a classical probability space, and you can define all, and then you cut some parts off, right? But
well, it's like just it behaves like classical with the different formulation definition of entropy. As soon as you define your entropy and uncertainty, that quantity that has to be conserved in a more geometric way, or just like simply as a distance.
Let's put it like this. What is your question? That is the things that I don't
Well,
understand.
just I was confused the whole like formulation of what an ensemble is, or what we call an ensemble in classical case and the quantum case, right? How corresponds
So
to
the ensemble in the quantum case is the block ball, right? You already know what it is. It's
well, like the whole space. That's for me. It's like a space for all possible states. How is it an ensemble? For me, ensemble is just one probability vector, which corresponds in this.
But you know what a density matrix is, right?
Yeah, it's just a block vector. One density metric is one block vector.
Right. So they can also be inside. It doesn't have to be outside. You know.
Yeah.
That's a density matrix. It's an ensemble. In quantum statistical mechanics, all ensembles are density matrices.
Right. So, but here, block sphere is not an ensemble; it's the state of all ensembles. Then
it's the space of all ensembles.
The space of all ensembles. It's just like low dimensional, so that you can visualize it in 3D. Like so
Right.
the only case that we can do it actually.
Yeah, in three with a three-dimensional state, you basically visualize the triangle, right? And then along the lines, you have another block sphere that connects the point, and every point you have a torus because it's the product of two circles, right? And with that, you can sort of generalize.
Yeah, that's 4 dimensions. That's basically when you have two qubits together, right?
No,
Not
that's when you have a three-state system.
Q-trade. Okay.
Yeah, Q3. There you go. I couldn't remember the name.
I
Yeah,
see.
in classical mechanics, for a discrete system, it would be the simplex, like the one you have here. But again, the ensemble space will require a definition of an entropy, because you have an entropy of the classical mechanics and quantum mechanics, and the entropy has to be convex with regard to the linear combination defined by the probability.
Yes.
Right? And
Your ensemble is just a vector. Inside of that simplex, you can define the Shannon entropy there. But you can also just compute the distance to the center of the tetrahedron, which is exactly like the same as von Neumann entropy, and conserved, right?
Yeah, that's called something else. I don't remember what they mean. Yeah, there is a one-to-one map between those two things.
Yeah.
Okay, I guess I still don't understand. So you can, I'm not saying that you can't make this construction. You can make this construction, but then every time that you have to calculate something, you have to be careful because you could potentially go outside of the space, and so you have to have all the
well, you make this when you actually make this for conversion to like arbitrary quantum process. Like if you do it to the unitary gate, to the unitary evolution, it's just going to be like some quasi-stochastic matrix that actually preserves the information. So it just corresponds to rotation, right? So you only constrain to those kind of processes for the unitary ones.
Okay.
But you can do it the same kind of conversion to any process. It's just going to be not some Hermitian matrix and your unitary one is just going to be some stochastic variant of that, or quasi-stochastic. And that
Lindblad and all that, yes. Quantum
yeah,
channel.
even Lindblad, like master equation in all its generality is going to just be converted to a single.
Maybe I have a question for you that I ask people I can never find. Can you tell me what are, on a qubit, what are all the operations that are allowed by a quantum channel?
Well,
so guys,
you mean some kind of visualization for all the space of those operations?
So give me a sec, guys. So I just got a call. I'm gonna have to attend.
Yeah, I should probably go. But if I can get an answer to this question,
yeah. So I don't want to cut the answer, but I really have to go now. So I just want to say, Gabriele, thank you so much. I appreciate your taking the time to understand my question. I understand a lot more, and I love your work. So congratulations on it. It's a great effort. I hope to contribute in some way or form in the future. So yeah. And
as I said, if you can go and find other like detail like that. For example, one of the things that I never quite understood is the difference between a Poisson manifold and a symplectic manifold.
I can help with that for sure. So I have it open in my tabs now, and I'll go read.
All right.
Bye, Gabriele. Thank you. Bye.
Thank you, Carlos.
Thanks. Well, I can tell you that you can essentially, using this construction, you can make it much more easier formulation of what the whole Lindblad master equation is, because after you vectorize, after you vectorize it, like after you vectorize your Hamiltonian, all those Lindblad jump operators, you can turn it into a single matrix, right? And this single matrix in this particular basis, which is probabilistic, is going to be just one another quasi-stochastic thing that you can just plug into differential equation involve. Right? So it's just one. Well, that's basically the answer. Maybe instead of thinking of
so I know that all the unitary evolutions are just rotational along the one axis.
Yes.
Okay, that's very good. I assume that I can pick an axis and project all the points to the axis, and that's a quantum channel. Like a quantum channel can do that. And I also assume that a quantum channel can project everything to the middle point. Right? Now, can a quantum channel project everything to any point in the block ball?
any point to any point, or I think it doesn't it's not allowed to expand. I think that's kind of
yes, that's clear. Like, but I should be able to. I know that I can project on the center point, and I know that I should be able to project to a pure state, because that would be a dissipative system. So everything is going to go in the ground state.
Yeah.
Now, can I take any point in the middle and have a quantum channel that projects everything to that point?
My intuition says yes, because it's like because if you think in the stochastic case, there is always a stochastic matrix, which is just a conditional probability table, right? If you just transform it into unitary, that's gonna translate to something that is not in the center, right? I think we can.
You can translate it and it still be so. Yeah, I don't see that. So you basically say I could take some quantum channel, translate it in inside the block sphere, but it's not just a translation, because the beginning changes as well. So I can't translate the beginning.
Not the translation. It's just you have to find a map. Like you have to find, in this probabilistic basis, you have to find the conditional probability table that maps your complete noisy uniform distribution into some different position, right? You can find those. If you can find this is just corresponds to some stochastic map. If that stochastic map, after transforming,
You say I use a stochastic map on those 4 points of the tetrahedron.
Yes, yeah.
So
that's stochastic map.
You're telling me that if any stochastic map on those 4 points, as long as it's contractive, as long as it doesn't blow up, right, is a valid quantum channel?
Well, they all contractive, yes. And I think maybe there's some constraint, I don't know, but
I know, but how do you do a rotation? Because a rotation would have to move those points somewhere else, so you're not going to be able to do a rotation.
No, rotation that's performs like stochastic map is a combination of a rotation and contraction. You can think of it like this way, right?
Okay. So I can do the rotation and I can do the contraction.
Yes.
Okay. And so would I be able to contract to a plane? Can I project to a plane?
I doubt that, because it's always going to be like a point.
Yeah, well, I can project to a line, right? I can contract to a line, I can contract to a point.
Yes.
Why is it that I can't contract to a plane?
Interesting. I don't know.
So this is kind of
Maybe
the thing that I'm trying to address, because I need to reverse engineer that part, and I still don't understand. Like I'd like to know what are all the space of possible flows inside a block ball for all the allowed quantum channels. So if you have a way for me to figure that out, that's something that I'm actively looking, and I haven't found anything in the. Oh, there you go. Is this what I'm looking for?
Yeah, that's what we have in the framework. Some particular set of channels that you can do, right? Not all of them, but at least here you can see what some of them are doing.
Okay, so are those yes, those are contracted. So the yellow thing is the contracted ball, right?
Yep.
Okay, so the 3 ones are contracting to the axis. The middle left is just contracting everything around the same point, and then yes, exactly, and then that one is contracting towards the point outside, and then this, what is this doing?
Some ellipsoid, some across
Okay.
particular axis, I guess. The x y axis or something like that.
Right now, I would basically need something that tells me that these are the only thing that I can do.
Yeah, well, we can think about how to do it. It's like we can just generate a random samples of channels. Like here, we can just
fine. No,
generate a random Liouvillean and
So-
make some similar pictures for some random Hermitian matrices and random Liouvilleans that they generate.
But this thing should be able to also do like symbolic manipulation, right?
Yes, it should. Like we can evolve our initial state. Is it how you do it? I guess you can do it like this. Like you can make an evolution. This state is parametric, right? It's like you can ask what is the state. It's maybe not physical. Why is it a null? Who knows? Let's try to see what actual block vector is. Okay. How can do it? We'll just do. Let's see how it actually evolves. I don't know. Plot. Maybe. Yeah, so it evolves to some weird thing. Hold on, Lioulin. Has to be Hamiltonian. Okay. That should correspond to more physical thing. All right. So that's something like this. But we need like some do it for all possible initial conditions.
Yeah, the looking at how the ball deforms, that's a good way to do it, because the map is linear, so it's once you know where the extreme points go, you know where everything goes. So that's interesting.
I know they can do.
Yeah, so I'm talking about. I asked this question to a bunch of people, and everybody have the same intuition that it can't become a plane, but nobody's ever able to tell me, yeah, why? What is the proper mathematical way to look at all the possible motions?
Yeah. Let's try something. Something weird. Just gonna plot an arrow. Okay. Go from this to this. T. No. So this is a right. It's like the whole surface. It's like x, y, z. At some point, it's like the whole vector.
Mm-hmm.
So what can we do? Should we do some parametric plot? I don't know. I don't think we should do it like right now.
Yeah, that's fine. That's fine. And like, if you had the answer already, would have been okay. But it's fine.
Yeah.
We should probably close anyway. I should probably go on and do everything. But you are confirming the same intuition that you can't.
I had a philosophical question for you.
Oh, yeah, go ahead. Yes.
So you had in a slide that if a system was mathematically describable, then it necessarily conserves quantities.
No.
No. Oh,
No.
I misread a slide then. Or you were talking about there was something in there of that nature.
Do you remember more or less when it was during?
I can say if I see it.
Should I share?
Yeah, Nick, can you?
Yeah, sure.
Unless you could.
No, something, but
yeah. It was in green text. What are these green text things?
You tell me when to stop.
Hold on, go forward. I might have been wrong. Hold on. Go to the beginning.
This one?
No, go to the beginning.
Like the beginning of the whole thing?
Wait.
Like the whole thing at the beginning of the first slide?
Uh-huh.
See if I
Might
can.
have been like slide 4 or 5 or something like that.
Okay, can I go? All right. Let's do this. It's gonna be easier than figuring out how to do it. Okay, so this is
Alright,
the first slide.
It was green text. It was green text. Are you going too fast? Hold on.
Well, I don't see any green text. So
Wait, what are you talking about? There's green text down there. See that?
yeah, but that doesn't say anything
Oh, yeah.
about. So there's no green text here. So there's this. There's a green text, but it has nothing to do with that. It's about entropy. Yeah, and then now we're going back to here. Yeah, we're back here. So there's this here. We're talking about a little bit of quantities, but it's not. Here's where I'm talking. This is the only place where I'm talking about measuring quantity. And here there are green texts. Yeah, that's it.
Okay. Well, it was something along the lines of conserved quantities and the ability for mathematics to describe reality, and the relationship between the two.
So the map between like math and so on, it's this slide over here, but it's not. I mean, there is okay. So there is this philosophical slide very much at the beginning, but where is it? This, but there's no green text.
Right, it was after this.
And then there is the part where I talk this, the boundary between the physics and the math, but it doesn't talk about conserved quantity. So.
All right.
Hey, shall we wrap it up?
Yeah, that was a great
yes.
discussion. Thank you, Gabriele.
Well, thank you for having me.
Lovely.
Thank you, Gabriele. Thank you.
See you next time.